The morning of December 8, 1942, marked the first recorded failure of an American flamethrower in combat. On Guadalcanal, as Marine Corporal James Tanaka of the Second Engineer Battalion crouched behind a fallen coconut palm, his M1 flamethrower refused to ignite. The hydrogen torch, supposedly reliable according to the Chemical Warfare Service Manual, produced nothing but a weak blue flicker. 60 yards ahead, Japanese machine gunners in a reinforced bunker continued their murderous crossfire, pinning down an entire rifle platoon. Tanaka yanked the battery connections, checked the hydrogen cylinder pressure, and tried again. Nothing. The electrical ignition system, the pride of American engineering, had failed at the moment of truth. Within minutes, a Japanese mortar round found the Marine positions. Tanaka and two other flamethrower operators became casualties not from enemy fire, but from their own weapons' inadequacy. This single incident would trigger a revolution in flamethrower technology that would reshape infantry tactics across 3 continents and 4 years of warfare. The story of how American engineers solved the ignition problem would ultimately produce the M2 flamethrower, a weapon so effective that Marine commanders on Iwo Jima would halt entire assaults until flame units arrived. But this innovation came at a terrible cost, measured in the lives of men who carried these 70-pound instruments of war into the most dangerous places on Earth. The path to the M2's cartridge ignition system began not in American laboratories, but in the frozen trenches of the Eastern Front, where German Flammenwerfer operators faced their own crisis of reliability. The winter of 1941 had exposed fatal flaws in every nation's flamethrower designs. What emerged from this crucible would determine who lived and died in the cave fighting of the Pacific War. The German weapons that had terrorized French defenders in 1940 were failing catastrophically in temperatures that plunged to -40 degrees Fahrenheit. Japanese flamethrowers, designed for tropical warfare, proved equally unreliable when tested in Manchurian winters. Italian flame units, already struggling with their flint ignition systems, found their weapons completely useless in mountain warfare conditions. Only through radical redesign would these weapons become the feared instruments that turned bunkers into crematoriums and caves into death traps. This is the untold story of how 4 nations raced to perfect the technology of projected fire, and how the solution that emerged would define the character of close-quarter combat for generations to come. Major Wilhelm Redmond stood in the pre-dawn darkness of July 29, 1915, watching his Pioneer make final preparations along the Hooge salient. The British trenches lay less than 5 yards away, close enough to hear individual conversations. Redmond's experimental Flammenwerfer units represented 18 months of development work by Richard Fiedler's engineering team, but this would be their first coordinated assault. At 3:15 that morning, Redmond gave the signal. 41 Flammenwerfer operators rose from the German trenches and sent streams of burning oil across no man's land. The psychological effect was immediate and devastating. British troops, who had weathered months of artillery bombardment with stoic determination, fled in panic from the advancing walls of flame. In less than 20 minutes, the Germans captured 600 yards of trenches and 800 prisoners. Casualties among the British, 751 men. This success at Hooge established the tactical principles that would govern flamethrower warfare for the next 30 years. Redmond understood that the weapon's primary value lay not in its killing power, but in its ability to force defenders from protected positions. Fire, unlike bullets or shrapnel, could flow around corners, seep into crevices, and reach spaces that conventional weapons could not touch. More importantly, few soldiers possessed the psychological fortitude to remain in position when faced with approaching flames. By 1918, German industry had produced over 700 different flamethrower models, ranging from one-man portable units to massive fortress installations with ranges exceeding 100 yards. The Wechselapparat, or Wex, introduced in 1917, weighed only 35 pounds and featured a self-igniting striker mechanism. This became the template for all future German flamethrower development. The Treaty of Versailles specifically banned German possession, manufacture, or importation of flamethrowers, testimony to their battlefield effectiveness. But when Adolf Hitler abrogated the treaty provisions in 1933, German engineers resumed development with 2 decades of accumulated experience. The lessons learned in the trenches of the Western Front would now be applied to create weapons suited for the mobile warfare doctrines of the Wehrmacht. At Kummersdorf, 25 kilometers south of Berlin, Colonel Walter Dornberger established the primary German flamethrower testing facility in 1932. Dornberger, who would later oversee V-2 rocket development at Peenemünde, understood that modern flamethrowers needed to support rapid offensive operations rather than static trench warfare. His research teams focused on reducing weight while maintaining range and fuel capacity. The Flammenwerfer 35, introduced in 1935, represented a compromise between the competing demands of mobility and effectiveness. At 79 pounds fully loaded, it carried 11.8 liters of Flammel 19, a mixture of gasoline and tar designed to burn longer and stick to targets better than pure gasoline. The hydrogen torch ignition system provided reliable lighting under normal conditions, with an effective range of 25 meters and a burn time of 10 seconds. Hermann Göring, as head of the Luftwaffe, placed the first production orders in 1932. By the beginning of 1939, German factories had delivered 1,000 flamethrowers to specialized Sturmpioneer units. These assault pioneers trained extensively in combined arms tactics, coordinating flame attacks with infantry advances, artillery support, and combat engineer operations. The early success of German flamethrowers in the 1940 campaign against France validated Dornberger's design philosophy. Sturmpioneer units breached the Maginot Line's fortifications by directing flame streams through embrasures and ventilation systems. French defenders, protected from artillery and machine gun fire, found themselves defenseless against weapons that could reach them in their deepest bunkers. But the true test came with Operation Barbarossa, the June 22, 1941 invasion of the Soviet Union. German planners expected a rapid campaign concluded before winter, making cold weather performance a secondary concern. This assumption would prove nearly fatal for Flammenwerfer operations. Oberstfreiter Hans Müller of the 3rd Sturmpioneer Company, attached to the 6th Army, recorded his experiences during the advance on Stalingrad. His unit's first winter operation, conducted in November 1941 near Rostov, demonstrated the catastrophic failure of hydrogen ignition systems in extreme cold. Of 12 Flammenwerfer 35s deployed, only 3 achieved successful ignition. The remainder produced weak flames that barely reached 10 meters before guttering out. Müller's personal account, preserved in Wehrmacht archives, describes the tactical consequences. The Ivan machine gun nest was 70 meters to our front, behind a concrete wall 2 meters thick. Our artillery had been pounding it for 2 hours without effect. When we moved forward with the Flammenwerfer, the weapon failed to light properly. The flame sputtered and died after 3 seconds. The Russians immediately opened fire, killing Feldwebel Hoffmann and wounding 2 others. We had to withdraw without taking the position. Similar failures occurred across the entire Eastern Front during the winter of 1941–42. German after-action reports documented ignition failure rates exceeding 60% when temperatures dropped below -10 degrees Celsius. The hydrogen in the ignition system froze, batteries lost power in extreme cold, and the electrical components became unreliable. This crisis forced German engineers to fundamentally redesign their flamethrower ignition systems. The Flammenwerfer 41, introduced in 1941, initially retained the hydrogen torch but incorporated improved cold weather components. However, field reports continued to document unacceptable failure rates, leading to the development of a cartridge-based ignition system similar to that used in signal flares. The cartridge ignition system represented a major breakthrough in flamethrower reliability. Instead of relying on electrical components and hydrogen gas, the new system used small pyrotechnic cartridges that ignited reliably in any weather condition. The operator loaded a cartridge into a chamber at the nozzle, and when the firing lever was actuated, a spring-loaded striker ignited the cartridge, which in turn lit the fuel stream. Hauptmann Friedrich Steiner of the 7th Sturmpioneer Company tested the improved system during the Battle of Kursk in July 1943. His unit's 12 Flammenwerfer 41s achieved a 96% ignition success rate across 5 days of continuous operations. The psychological impact on Soviet defenders was immediate and decisive. Steiner reported, The flame weapons cleared 3 fortified positions that had resisted our infantry attacks for 48 hours. Enemy casualties were light, but the positions were abandoned immediately upon the first flame attack. German production of the Flammenwerfer 41 reached 70,000 units between 1941 and 1945. These weapons were distributed not only to Army Sturmpionier units, but also to Luftwaffe ground forces, Kriegsmarine coastal defense units, and police battalions. Additionally, 1,300 flamethrowers were allocated to Germany's Axis allies, including Italy, Hungary, Romania, and Finland. The success of the cartridge ignition system influenced German development of defensive flamethrowers as well. The Flammenwerfer 42, a single-shot defensive weapon, used similar pyrotechnic ignition principles. 50,000 of these devices were deployed along the Atlantic Wall and other fortified positions by June 1944. Each Flammenwerfer could be buried alongside conventional mines and triggered by tripwire or command detonation, creating instant flame barriers across likely approach routes. German tactical doctrine emphasized the psychological value of flamethrowers over their killing power. Wehrmacht training manuals instructed operators to use short bursts to conserve fuel while maximizing terror effects. The thick black smoke produced by burning Flammel 19 created a screening effect that aided infantry advances, while the distinctive whoosh of ignition often caused enemy defenders to abandon positions before flames actually reached them. Oberst Wolfgang Pickert, who commanded German flamethrower training at Kummersdorf, developed the tactical principles that governed Flammenwerfer employment throughout the war. His doctrine emphasized surprise, speed, and close coordination with supporting arms. Flamethrower teams approached targets under cover of darkness or smoke, moved to within effective range as quickly as possible, delivered short bursts to neutralize resistance, and immediately withdrew to allow infantry to occupy the position. The effectiveness of these tactics was demonstrated during urban fighting in Warsaw, both during the Ghetto Uprising in 1943 and the General Warsaw Uprising in 1944. German forces used flamethrowers systematically to clear buildings, with Sturmpioneer teams moving from room to room behind advancing infantrymen. The psychological impact proved so severe that many Polish defenders surrendered immediately upon hearing the distinctive sound of flamethrower ignition. As the war turned against Germany, flamethrower production continued at maximum capacity. The Einstas Flammenwerfer 46, a lightweight single-shot weapon weighing less than 8 pounds, was developed for Volkssturm units defending the homeland. These simplified devices used the same cartridge ignition system as the larger weapons but carried only enough fuel for one brief burst. Thousands were manufactured in the final months of the war for use by hastily trained civilian defenders. The German flamethrower program's greatest contribution to military technology was the cartridge ignition system. This innovation solved the reliability problems that had plagued all early flamethrowers and provided the foundation for more advanced designs developed by other nations. The psychological warfare aspects pioneered by Redman and refined by later German tacticians established flamethrowers as essential weapons for close-quarter combat. However, German flamethrower development also revealed the fundamental limitations of the weapon. Despite their terror value, flamethrowers remained short-ranged, cumbersome, and dangerous to operate. The operator's silhouette, marked by distinctive tank configuration and projector outline, made him an immediate target for enemy marksmen. German units attempted to disguise flamethrowers by modifying the projector to resemble a rifle, but experienced troops could usually identify the weapon by its operator's movement patterns and protective equipment. The vulnerability of flamethrower operators became a critical factor in German tactical planning. Standard procedure called for each flame team to include 2 riflemen for protection, effectively requiring 3 soldiers to operate a single specialized weapon. This manpower requirement limited the number of flamethrowers that could be deployed and concentrated valuable specialist personnel in high-risk positions. German experiences on the Eastern Front also demonstrated that flamethrowers were primarily weapons of offense rather than defense. While the Flammenwerfer 42 showed some promise as a defensive tool, portable flamethrowers were most effective when used aggressively against fixed positions. This offensive orientation made them less valuable as the Wehrmacht increasingly fought defensive actions from 1943 onward. Nevertheless, German flamethrower innovations provided the technical foundation for American developments that would follow. The cartridge ignition system, cold weather modifications, and tactical employment principles developed by German engineers influenced Allied weapon design throughout the remainder of the war. The race to improve flamethrower reliability had begun, and the solution would ultimately determine the outcome of cave fighting across the Pacific theater. Captain Hiroshi Nakamura of the Imperial Japanese Army's Engineering Regiment stood in the ruins of Port Arthur, studying the Russian fortifications that had cost Japan so dearly during the Russo-Japanese War of 1904 to 1905. The concrete bunkers and interconnected trenches had withstood months of artillery bombardment, forcing Japanese infantry to assault prepared positions with devastating casualties. Nakamura, serving as a military observer in Europe during the Great War, had witnessed German flamethrower attacks and understood their potential for solving Japan's tactical problems. Upon returning to Tokyo in 1920, Nakamura submitted a detailed report to the Army General Staff recommending immediate development of Japanese flamethrower capabilities. His analysis emphasized that Japan's strategic position, with its need to assault island fortifications and coastal defenses, made flamethrowers particularly valuable for the Imperial Army. The report noted that conventional artillery was often ineffective against reinforced concrete positions, but projected fire could reach defenders in spaces immune to shell fragments. The Japanese military attaché in Berlin, Colonel Kenji Ishiwara, provided additional intelligence on German flamethrower developments throughout the 1920s. His reports described technical specifications, tactical employment methods, and production figures for various Flammenwerfer models. This intelligence-gathering operation gave Japanese engineers access to the most advanced flamethrower technology available, forming the foundation for indigenous development programs. Initial Japanese experiments began at the Tokyo Imperial University Engineering Department in 1930. Professor Yoshio Nishina, working under contract to the Army Technical Bureau, developed prototypes based on German designs but adapted for tropical service conditions. The primary challenge involved creating ignition systems that would function reliably in high-humidity environments while remaining simple enough for field maintenance by infantry units. The Type 93 flamethrower, officially adopted in 1933, represented Japan's solution to these challenges. At 24.9 kilograms fully loaded, it was significantly lighter than contemporary German models. The fuel capacity of 11.4 liters provided 10 to 12 seconds of continuous firing, sufficient for most tactical applications while minimizing operator burden. The ignition system represented the most innovative aspect of Japanese flamethrower design. Instead of hydrogen torches or electrical systems, Japanese engineers developed a revolver-like mechanism using blank ballistite cartridges. A magazine housed beneath the projector nozzle contained 10 cartridges, each capable of reliable ignition regardless of weather conditions. When the operator rotated the firing handle 90 degrees, the magazine advanced to the next cartridge, the striker was released, and the cartridge fired, igniting the fuel stream. Lieutenant Colonel Saburo Hayashi, commanding the 1st Engineering Regiment, conducted extensive testing of the Type 93 during maneuvers in Manchuria throughout 1934. His reports praised the weapon's reliability, noting ignition success rates exceeding 95% across diverse weather conditions. The cartridge system proved particularly effective in winter operations, where German-style hydrogen ignition systems would have failed completely. The fuel mixture used in Japanese flamethrowers consisted of 50% benzene and 50% crude oil, creating a substance that burned intensely while adhering to surfaces. This composition provided advantages over pure gasoline mixtures, as it was less likely to be extinguished by wind or impact and continued burning for several minutes after initial contact. The psychological effect on enemy troops was enhanced by the persistent nature of the flames and the characteristic black smoke produced by burning crude oil. Japanese tactical doctrine emphasized the shock value of flamethrowers over their direct killing power. Army training manuals instructed operators to use the weapon's terror effect to force enemy abandonment of positions, rather than attempting to kill defenders with fire. This approach maximized the psychological impact while conserving precious fuel and reducing operator exposure time. The first combat employment of Japanese flamethrowers occurred during the Second Sino-Japanese War, beginning in July 1937. The assault on the Marco Polo Bridge near Beijing demonstrated the weapon's effectiveness against Chinese defensive positions. Captain Tetsuo Yamada of the 3rd Engineering Company reported using flamethrowers to clear reinforced positions that had resisted infantry attacks for 18 hours. Chinese defenders, equipped primarily with rifles and light machine guns, possessed no effective countermeasures against flamethrower attacks. The psychological impact proved so severe that entire battalions abandoned positions upon witnessing flame attacks against neighboring units. Japanese commanders quickly recognized that a single flamethrower team could often accomplish what required company-sized infantry assaults, dramatically reducing Japanese casualties while accelerating operational tempo. The success in China led to expanded flamethrower production and tactical development. By 1939, each Japanese infantry division's engineering regiment was equipped with between 6 and 20 flamethrowers, organized into specialized companies with dedicated training programs. Flamethrower operators received intensive instruction not only in weapon employment but also in battlefield movement, target selection, and coordination with supporting units. Major Ichiro Watanabe, who commanded flamethrower operations during the Battle of Namenhin against Soviet forces in 1939, provided detailed accounts of tactical employment against determined opposition. Unlike Chinese forces, Soviet troops possessed anti-tank weapons and coordinated artillery support, making flamethrower operations significantly more dangerous. Watanabe's unit suffered 40% casualties during 3 days of fighting, but succeeded in breaking Soviet defensive lines that had held for 2 weeks. The Namenhin experience revealed critical limitations in Japanese flamethrower tactics. Soviet forces targeted flamethrower operators with concentrated rifle fire, recognizing their tactical importance. The distinctive silhouette of the Type 93 made operators easily identifiable at ranges exceeding 200 meters, well beyond the weapon's effective range of 22 meters. This vulnerability required fundamental changes in employment methods. Colonel Masanobu Tsuji, serving as a staff officer with the Guangdong Army, developed new tactical procedures based on Namenhin lessons. His directives emphasized deception, concealment, and close coordination with supporting fires. Flamethrower teams would approach targets under cover of smoke or darkness, using terrain features to mask their movement until reaching optimal firing positions. Simultaneous attacks by multiple teams prevented enemy forces from concentrating defensive fires against individual operators. The outbreak of the Pacific War in December 1941 provided Japanese flamethrowers with their greatest test. The assault on Wake Island demonstrated both the potential and limitations of the weapon in amphibious operations. Major Kunio Deveru led flamethrower teams against American defensive positions, achieving tactical success but suffering heavy casualties in the process. American defenders, armed with modern weapons and trained in anti-tank tactics, proved more formidable opponents than Chinese forces. Marine rifle fire and automatic weapons killed several Japanese flamethrower operators before they could reach effective range. However, successful flame attacks against American bunkers proved devastating, with several positions abandoned immediately after brief exposure to fire. The Battle of Bataan provided Japanese forces with extensive opportunities to employ flamethrowers against prepared American and Filipino defensive positions. Captain Hiroshi Takeuchi of the 14th Engineering Regiment documented systematic use of flame weapons to reduce fortified positions throughout the peninsula. His reports describe coordinated attacks involving artillery preparation, smoke screens, infantry suppression, and flame assaults. Filipino and American defenders, lacking adequate anti-tank weapons and artillery support, proved vulnerable to Japanese flamethrower tactics. Takeuchi's unit achieved tactical success rates exceeding 80%, with most target positions abandoned within minutes of initial flame contact. The psychological effect extended beyond immediate targets, as word of flame attacks spread through defending units and reduced overall morale. The successful employment of flamethrowers in the Philippines campaign led to their inclusion in Japanese defensive planning as Allied forces began their counteroffensive. However, the transition from offensive to defensive operations revealed fundamental weaknesses in Japanese flamethrower doctrine. Weapons designed for assault operations proved less effective when used to defend static positions against attacking forces. The Type 100 flamethrower, introduced in 1940, incorporated lessons learned from early war operations. The primary improvement involved redesigning the nozzle system to provide greater range and improved flame characteristics. The basic fuel system and cartridge ignition mechanism remained unchanged, having proven reliable under combat conditions. Lieutenant General Tadamaki Kurabayashi, appointed to command the defense of Iwo Jima in 1944, incorporated flamethrowers into his defensive preparations despite their primary design for offensive operations. His defensive doctrine called for using flame weapons to defend key positions, particularly cave mouths and tunnel entrances that formed the backbone of Japanese defensive positions. The Battle of Iwo Jima would provide the ultimate test of Japanese flamethrower technology against an opponent equipped with superior weapons and extensive flamethrower experience. American forces, by February 1945, possessed advanced flame weapons of their own and had developed specific tactics for countering Japanese flame attacks. Colonel Takechi Nishi, commanding Japanese tank units on Iwo Jima, reported minimal success with defensive flamethrower employment against American assault teams. American forces used concentrated rifle fire, automatic weapons, and their own flamethrowers to neutralize Japanese flame positions before they could effectively engage attacking troops. The defensive advantage traditionally enjoyed by prepared positions was negated when both sides possessed effective flame weapons. Japanese flamethrower operators on Iwo Jima faced American forces equipped with the newly introduced M2 flamethrower, a weapon with superior range, reliability, and fuel capacity. American flame tanks provided additional capabilities that Japanese forces could not match. The technological advantage had shifted decisively in favor of American forces, making Japanese flamethrower operations extremely hazardous. Private First Class Kuniaka Yamada of the 109th Infantry Battalion described his experiences operating a Type 100 flamethrower during the defense of Hill 382 on Iwo Jima. His account, recorded after capture in March 1945, describes repeated unsuccessful attempts to engage American assault teams. The American flame weapons had much greater range than ours. They could attack our positions from distances where our weapons could not reach them. When we tried to move closer, their rifles and automatic weapons killed our operators. The technological disparity between Japanese and American flamethrowers by 1945 reflected broader industrial and scientific advantages that determined the war's outcome. While Japanese engineers had created innovative and reliable weapons within their resource constraints, American industrial capacity and research capabilities produced superior equipment in overwhelming quantities. Nevertheless, Japanese flamethrower development made significant contributions to military technology. The cartridge ignition system proved more reliable than early German electrical systems and influenced American development of the M2 flamethrower. The emphasis on lightweight construction and tropical service reliability provided valuable lessons for post-war equipment design. The psychological warfare aspects pioneered by Japanese tacticians demonstrated flamethrowers' value beyond their direct killing power. The systematic use of flame weapons to force enemy abandonment of positions rather than attempting to kill defenders became standard doctrine for all nations. This approach maximized the weapon's terror effect while conserving fuel and reducing operator exposure. Japanese flamethrower operations also revealed the importance of combined arms tactics in flame warfare. Successful attacks required coordination between artillery support, smoke screens, infantry suppression, and flame assault teams. This integration became increasingly sophisticated as Japanese forces gained combat experience, leading to tactical innovations adopted by other armies. The vulnerability of flamethrower operators, clearly demonstrated in Japanese combat experience, influenced equipment design and tactical procedures throughout the war. The need for concealment, protection, and multiple approach routes became fundamental principles governing flamethrower employment. These lessons shaped American tactical development and contributed to the design of vehicle-mounted flame systems. The Japanese experience demonstrated that flamethrowers were primarily weapons of offense, most effective when used aggressively against static targets. Defensive employment, while possible, required specific tactical conditions and could not substitute for conventional defensive weapons. This understanding influenced post-war doctrinal development and equipment procurement decisions. Finally, Japanese flamethrower development illustrated the relationship between tactical requirements and technological solutions. The need to assault fortified positions drove innovation in ignition systems, fuel mixtures, and employment methods. These technological advances, in turn, enabled new tactical possibilities and operational concepts that extended far beyond the original requirements. Colonel Alessandro Fioravanti stood among the ruins of Ethiopian fortifications at Adawa, where Italian forces had suffered their most humiliating defeat 40 years earlier. As commander of the 5th Engineer Regiment during Mussolini's 1935 invasion of Ethiopia, Fioravanti possessed the weapons that earlier Italian commanders had lacked: portable flamethrowers and flame-throwing tankettes capable of reducing any fortification to ashes within minutes. The Second Italo-Ethiopian War marked Italy's first systematic employment of modern flamethrowers, demonstrating both their tactical value and the industrial limitations that would plague Italian weapons development throughout World War II. The Lanciafium Spalleggiato Modello 35, adopted by the Royal Italian Army in 1935, represented a conventional design heavily influenced by German models but adapted for Italian production capabilities and tactical requirements. At 56 pounds fully loaded, the Modello 35 required two-man crews due to its weight and cumbersome operation. The twin cylindrical tanks, each internally divided between fuel and nitrogen propellant, provided a maximum range of 27 feet with approximately 15 seconds of burning time. The Flint ignition system, while simple and inexpensive to manufacture, proved unreliable under combat conditions and required frequent maintenance by trained specialists. Lieutenant Colonel Giuseppe Bottai, commanding the 3rd Flame Company during the assault on Makael, documented the weapon's effectiveness against Ethiopian defensive positions. His after-action report noted, "The psychological effect of the flame weapons exceeded all expectations. Ethiopian defenders, who had demonstrated considerable courage against rifle fire and artillery bombardment, abandoned their positions immediately upon witnessing flame attacks. Entire companies surrendered without resistance after observing the fate of flame-attacked positions." The success in Ethiopia validated Italian flamethrower doctrine but also revealed significant technical deficiencies. The Flint ignition system failed in approximately 20% of employment attempts, forcing operators to expose themselves while attempting repairs under enemy fire. The short range of 27 feet required flame teams to approach targets closely, making them vulnerable to small arms fire from prepared positions. These limitations drove development of the Modello 40, introduced in 1940 with an electrical ignition system designed to improve reliability. However, Italian industrial capacity constraints limited production quality, and the new ignition system proved even less reliable than the original Flint mechanism. Field reports documented failure rates exceeding 30%, making the weapon unreliable for critical tactical missions. Major Emilio Grazioli, serving with the R8 Armored Division in North Africa, described typical Modello 40 performance during the 1941 Crusader operations. "The electrical ignition failed completely during our assault on British positions near Bir el Gobi. 3 of our 4 flamethrowers could not achieve ignition, forcing us to assault prepared positions with conventional weapons. The attack failed with heavy casualties that flame weapons might have prevented." Italian engineers recognized that technical improvements alone could not solve the fundamental problems of man-portable flamethrowers. The concept of mounting flame weapons on armored vehicles had originated during the Great War, but Italian designers were among the first to create practical flame tanks suitable for mobile operations. The L3LF, based on the Carro Veloce L3/33 tankette, entered service in 1935 as the world's first production flame tank. The L3LF carried 500 liters of flame fuel in an armored trailer, providing range and endurance far exceeding man-portable weapons. The flamethrower nozzle replaced one of the tankette's machine guns, while fuel delivery used a pump driven by the vehicle's transmission. This arrangement provided a maximum range of 40 meters, though some sources credit ranges up to 100 meters under optimal conditions. Captain Amadeo Guille, commanding a flame tankette platoon during the 1936 Ethiopian campaign, reported remarkable success against fortified positions. His unit's 6 L3LF tankettes reduced 12 Ethiopian strongpoints in 4 days of operations, suffering no casualties while capturing over 300 prisoners. The psychological impact proved so severe that Ethiopian forces began abandoning positions upon merely sighting Italian armor, whether flame-equipped or not. The Spanish Civil War provided Italian flame weapons with their first test against European opponents equipped with modern anti-tank weapons. The Corps of Volunteer Troops deployed both man-portable flamethrowers and L3LF flame tankettes in support of nationalist forces, encountering Soviet-supplied T-26 tanks and anti-tank guns operated by International Brigade volunteers. Major Carlo Rossi, commanding Italian flame units during the Battle of Guadalajara in March 1937, discovered that Republican forces possessed effective countermeasures against flame attacks. Soviet anti-tank guns, positioned to cover likely approach routes, destroyed 3 L3LF tankettes before they could reach effective range. Republican infantry, trained in anti-tank tactics, used concentrated rifle fire to kill several Italian flamethrower operators. The Spanish experience revealed fundamental vulnerabilities in Italian flame weapons that would plague their employment throughout World War II. The L3LF's thin armor, adequate against rifle fire in Ethiopia, proved insufficient against dedicated anti-tank weapons. The pump system, driven by the vehicle's transmission, was so weak that crews were instructed not to operate the flamethrower while moving at full speed, fearing the flame stream might ignite the vehicle itself. These technical limitations became critical when Italy entered World War II in June 1940. Italian flame units, deployed along the Alpine front against French fortifications, achieved some tactical success but suffered heavy casualties when French forces concentrated artillery fire against the distinctive flame tankettes. The L3LF's low silhouette provided some protection, but the fuel trailer made concealment difficult and created additional vulnerabilities. Colonel Ferdinando Zanussi, commanding Italian flame operations during the brief war with France, noted the psychological effect of flame weapons on French defenders. The Maginot Line bunkers, impervious to artillery bombardment, were quickly abandoned when our flame tanks approached firing positions. However, the French artillery, directed by trained observers, destroyed most of our flame vehicles before they could complete their missions. The German invasion of the Soviet Union in June 1941 provided Italian flame units with extensive combat opportunities on the Eastern Front. The Armyr Italian Army in Russia included flame-equipped units assigned to assault fortified Soviet positions. The vastly different conditions on the Eastern Front, extreme temperatures, improved Soviet anti-tank weapons, and experienced Red Army defenders created new challenges for Italian flame warfare. Lieutenant Colonel Mario Carloni, commanding the Torino Division's Flame Company, documented the complete failure of Italian flamethrowers during winter operations near Stalingrad. The electrical ignition systems in the Modello 40 flamethrowers froze completely, while the flint systems in older models became unreliable due to moisture and temperature extremes. Of 18 flamethrowers deployed, only 2 achieved successful ignition during December 1942 operations. The L3LF flame tankettes proved equally unsuitable for Eastern Front conditions. The weak pump system, already marginally adequate in temperate climates, lost effectiveness completely in sub-zero temperatures. Soviet anti-tank rifles and artillery destroyed most Italian flame vehicles before they could approach effective range, while the fuel trailers created logistical nightmares in the difficult supply conditions of the Russian front. Italian flame units achieved their greatest success in the Mediterranean theater, where conditions favored their limited capabilities and technical shortcomings were less critical. The 1941 operations in Yugoslavia and Greece provided opportunities for effective employment against opponents lacking modern anti-tank weapons and adequate artillery support. Major Giulio Douhet, grandson of the famous air power theorist, commanded L3LF operations during the invasion of Yugoslavia in April 1941. His flame tankettes proved effective against Yugoslav defensive positions, particularly in urban areas where their short range was less disadvantageous. The psychological impact on Yugoslav defenders, many of whom had never encountered flame weapons, contributed significantly to the rapid collapse of organized resistance. Greek forces, better equipped and more determined than their Yugoslav counterparts, provided stiffer resistance to Italian flame attacks. However, the mountainous terrain of the Greek-Albanian front favored flame weapons, as defenders were often positioned in caves and rock formations vulnerable to flame attack. Italian units reported particular success using man-portable flamethrowers to clear mountain positions that had resisted infantry assault. The development of the Lanciafium Mod 41 represented Italian efforts to address the reliability problems that plagued earlier models. The new weapon featured an improved electrical system designed to function under adverse conditions, though weight remained problematic at the original 56 pounds fully loaded. Production was limited by Italy's industrial constraints and competing demands for strategic materials. For specialized units, Italian engineers developed the Lanciafium Mod 41 d'Assalto, a lighter weapon designed for paratrooper and assault troops. This rifle, like flamethrower, weighed significantly less than standard models but possessed extremely limited range and fuel capacity. It was intended for close-quarter combat in urban environments or specialized operations where conventional flamethrowers were impractical. The Lanciafium Carrolato Modello 42 represented Italy's attempt to create a heavy flamethrower system for engineering units. Mounted on a wheeled carriage, this weapon provided greater range and fuel capacity than man-portable models but required vehicle transportation and specialized crews. Production remained limited throughout the war due to resource constraints and competing priorities. Italian flame weapon production peaked in 1940 with approximately 1,500 flamethrowers in service across all models. However, the entry of the United States into the war dramatically changed the strategic situation, making Italian industrial limitations increasingly critical. Advanced American and British weapons systems outclassed Italian equipment, while Allied material superiority made Italian resistance increasingly futile. The Armistice of September 1943 effectively ended Italian flame weapon development, though some units continued operating under German control. The Italian Social Republic, established in northern Italy under German auspices, inherited limited flame weapon stocks but lacked the industrial capacity for significant production. Most remaining Italian flamethrowers were absorbed by German forces or destroyed during the chaotic period following the armistice. Finnish forces received 176 Italian flamethrowers in 1939, using them effectively during the Winter War against Soviet forces. The weapons, redesignated Lekenheiten M/40 by Finnish forces, proved more reliable in Arctic conditions than their Italian operators had experienced in temperate climates. Finnish tactical employment emphasized concealment and surprise, maximizing the psychological effect while minimizing operator exposure. The Italian flame weapon program's most significant contribution to military technology was the development of practical flame tanks. The L3LF, despite its limitations, demonstrated that vehicle-mounted flamethrowers could provide capabilities impossible with man-portable weapons. This concept influenced German, American, British, and Soviet flame tank development throughout the war. Italian tactical innovations in urban flame warfare provided valuable lessons for other armies. The systematic use of flame weapons to clear buildings, developed during operations in Yugoslavia and Greece, became standard procedure for urban assault operations. Italian emphasis on psychological warfare aspects influenced doctrine development in other nations, particularly regarding the terror effects of flame weapons on inexperienced troops. The technical failures of Italian flamethrowers illustrated the relationship between industrial capacity and weapons effectiveness. Limited resources forced compromises in design and manufacturing that reduced reliability and combat effectiveness. These lessons influenced post-war procurement policies and highlighted the importance of adequate testing and quality control in weapons development. Italian experience demonstrated that flame weapons required extensive training and specialized maintenance to achieve acceptable reliability. The complexity of ignition systems, fuel handling procedures, and tactical employment meant that flame units needed dedicated specialists and could not be operated effectively by conventional infantry. This requirement for specialized personnel limited the number of flame weapons that could be fielded and concentrated valuable human resources in high-risk positions. The vulnerability of flame-equipped vehicles, clearly demonstrated by L3LF combat experience, influenced armored fighting vehicle design throughout the war. The need for adequate protection, reliable fuel systems, and effective countermeasures against anti-tank weapons became fundamental requirements for successful flame tank design. These lessons shaped American, British, and Soviet flame vehicle development and contributed to improved tactical employment methods. Colonel William Porter stood in the wreckage of the Chemical Warfare Service testing facility at Edgewood Arsenal, Maryland, examining the twisted remains of the latest M1 flamethrower prototype. The January 1943 test had ended catastrophically when the electrical ignition system malfunctioned, igniting fuel vapors within the weapon itself and severely burning 2 technicians. This marked the 7th major failure in 3 months of testing, confirming what frontline reports from the Pacific had already made clear. American flamethrower technology lagged dangerously behind battlefield requirements. The failure at Edgewood crystallized mounting frustration within the U.S. Army's Chemical Warfare Service over the inadequacy of American flame weapons. Reports from Guadalcanal, where Marines had experienced repeated M1 ignition failures during critical combat operations, demonstrated that American lives were being lost due to inferior equipment. The hydrogen torch ignition system, seeming advanced in laboratory conditions, proved unreliable under the stress, humidity, and chaos of tropical warfare. Major George Unmacked, recently assigned to oversee flamethrower development at the Chemical Warfare Service's Pacific Area Headquarters, had reviewed every after-action report from American flame operations since Pearl Harbor. The pattern was unmistakable. M1 flamethrowers failed to ignite in approximately 40% of combat employment attempts. When ignition was achieved, the weapon's 15-meter range forced operators to expose themselves to enemy fire at distances where rifle-armed defenders held significant advantages. The M1's 72-pound weight, distributed between fuel tanks and propellant systems, exhausted operators during approach movements across difficult terrain. Pacific theater conditions, dense jungle, coral ridges, volcanic sand, and tropical heat made carrying the heavy weapon a grueling ordeal that left operators too fatigued for accurate weapon employment. The distinctive silhouette of the M1's hydrogen cylinder, mounted parallel to the projector tube, made concealment impossible and provided Japanese snipers with easily identifiable targets. Captain Robert Patterson, commanding the 2nd Marine Engineer Battalion's flame section during the Bougainville campaign, documented typical M1 performance in his March 1943 after-action report. Of 12 flamethrowers deployed during the assault on Hill 260, only 7 achieved successful ignition. 3 operators were killed attempting to repair their weapons under enemy fire. The remaining functional weapons exhausted their fuel without achieving tactically significant results due to insufficient range and poor flame characteristics. These battlefield failures prompted urgent research into alternative ignition systems and fuel compositions. Dr. Louis Fieser of Harvard University, working under contract to the Office of Scientific Research and Development, had developed napalm, a thickening agent for gasoline that dramatically improved flame characteristics. However, the existing M1 platform could not handle the higher pressures required to project thickened fuel effectively. The M1A1, introduced in June 1943, represented an interim solution incorporating napalm fuel and improved pressure systems. The weapon's range increased to 45 meters, more than doubling the M1's effectiveness, while the sticky characteristics of napalm allowed flame streams to adhere to surfaces and continue burning. Weight decreased to 65 pounds, providing marginal improvement in operator mobility. However, the M1A1 retained the problematic hydrogen ignition system that had plagued its predecessor. Lieutenant Colonel Louis Puller, commanding the 1st Battalion, 7th Marines during the New Britain campaign, observed a demonstration of the new weapon and delivered his famous assessment. "Where do you put the bayonet on the damn thing?" His skepticism reflected widespread Marine Corps concerns about flamethrower reliability and tactical utility. The breakthrough came from an unexpected source: captured German equipment analysis conducted by the Technical Intelligence Division. German Flammenwerfer 41 weapons recovered from North African battlefields incorporated cartridge ignition systems that functioned reliably under all conditions encountered during testing. The pyrotechnic cartridges ignited consistently regardless of temperature, humidity, or mechanical shock, eliminating the electrical components that made earlier systems vulnerable. Major William Smith, Chief of the Chemical Warfare Service's Research and Development Division, immediately recognized the potential of cartridge ignition for American flamethrowers. His team began developing similar systems using readily available signal flare components, creating a mechanism that was simpler, more reliable, and less expensive than hydrogen torch systems. The cartridge magazine could hold sufficient rounds for extended operations while adding minimal weight to the overall weapon. The experimental E3 flamethrower, tested at Dugway Proving Ground in Utah during summer 1943, incorporated cartridge ignition with redesigned fuel systems optimized for napalm. Range exceeded 40 meters consistently, ignition reliability approached 98%, and the weapon could function after submersion in salt water, a critical requirement for amphibious operations. Colonel Unmacked, now commanding Pacific Area Chemical Warfare Service operations from headquarters at Schofield Barracks in Hawaii, received authorization to begin limited production of the E3 design in November 1943. However, the weapon's designation was changed to M2 to reflect its role as the standard replacement for earlier models. Initial production contracts called for delivery of 500 weapons by March 1944. The first M2 flamethrowers reached Marine units preparing for Operation Forager, the assault on the Mariana Islands. Captain James Day of the 2nd Battalion, 24th Marines conducted extensive training with the new weapons during rehearsals at Maui in May 1944. His evaluation report praised the M2's reliability and effectiveness. Ignition success rate exceeded 95% across 100 test firings. Range consistently exceeded 40 meters with good flame density. Operators report reduced fatigue due to improved weight distribution. The Battle of Saipan provided the M2's combat debut, demonstrating capabilities that transformed American assault tactics. Technical Sergeant Mitchell Page, operating an M2 during the assault on Mount Tapasho, reported clearing 3 Japanese cave positions in 15 minutes, targets that had resisted infantry and artillery attacks for 18 hours. The psychological effect on Japanese defenders proved as devastating as the physical damage, with entire positions abandoned upon witnessing flame attacks. Production of the M2 accelerated throughout 1944 as combat reports confirmed its effectiveness. The Ronson Company, previously manufacturer of cigarette lighters, converted its production facilities to manufacture flame gun components. The Liquid Carbonic Corporation provided pressurization systems, while dozens of smaller contractors produced specialized components under Chemical Warfare Service supervision. By December 1944, American industry had delivered over 15,000 M2 flamethrowers to combat units, surpassing the combined production of M1 and M1A1 models. The weapon's success prompted development of vehicle-mounted variants, leading to the flame tank programs that would prove decisive in final Pacific operations. Staff Sergeant Franklin Williams, later awarded the Medal of Honor for his actions on Iwo Jima, provided detailed accounts of M2 employment during some of the war's most intense fighting. His February 23, 1945 action, clearing 7 Japanese positions in 4 hours, demonstrated the weapon's tactical impact when operated by trained specialists supported by coordinated infantry teams. The M2 gave us capabilities we never had before, Williams recalled in post-war interviews. The range let us engage targets from positions where we had some protection. The ignition worked every time, which meant we could count on the weapon when lives depended on it. Most importantly, the Japanese feared it more than any other weapon we carried. The Marine Corps' organizational structure evolved to accommodate increased flamethrower capabilities. The D-Series division of 1943 included only 24 flamethrowers, all assigned to the Engineer Battalion. By 1944, the F-Series division carried 243 flamethrowers, distributed throughout infantry regiments, with each regiment receiving 81 weapons for organic flame capabilities. This distribution reflected new tactical concepts emphasizing flamethrowers as essential infantry weapons rather than specialized engineering equipment. Rifle companies incorporated flame teams into standard assault procedures, using concentrated fire to suppress enemy positions while flamethrower operators approached effective range. The technique, called corkscrew and blowtorch by Marines, became standard procedure for reducing fortified positions. Technical improvements continued throughout 1944 and 1945 as combat experience revealed opportunities for enhancement. The M2A1, introduced in early 1945, featured improved nozzle design and enhanced fuel systems. The M2A2 incorporated lessons learned from cold weather operations in the Aleutians, though most production remained focused on Pacific theater requirements. American flame tank development, centered at Colonel Unmack's facility in Hawaii, produced revolutionary capabilities that complemented man-portable weapons. The conversion of Sherman medium tanks to flame configuration required extensive modifications, with each installation consuming 150 pounds of welding rod and over 1,000 electrical connections. Cost per conversion approached $25,000, equivalent to nearly $300,000 in modern currency. The CBH-1 and CBH-2 flame tanks, developed by Navy CB specialists working under Chemical Warfare Service direction, provided range and protection impossible with portable weapons. Operating at 300 pounds per square inch pressure, these systems achieved 400-foot range with 270-degree traverse capability. 8 flame tanks supported Marine operations on Iwo Jima, proving so effective that assault units would halt attacks until flame support became available. Maintenance and logistics requirements for American flamethrowers demanded specialized support organizations. Chemical service companies, initially organized for gas warfare duties, assumed responsibility for flamethrower maintenance, fuel preparation, and operator training. These units included specialists in mechanical repair, fuel chemistry, and tactical employment, providing expertise that conventional infantry units could not develop independently. Fuel production became a critical factor limiting flamethrower employment. Napalm manufacture required specialized facilities and trained personnel, while transportation and storage created unique logistical challenges. The Chemical Warfare Service established production facilities in Hawaii, Australia, and forward areas to minimize supply lines and ensure adequate stocks for sustained operations. Quality control proved essential for maintaining weapon reliability under combat conditions. Chemical Warfare Service inspection teams tested every flamethrower before shipment, checking ignition systems, fuel systems, and pressure regulation components. Weapons that failed inspection standards were returned to manufacturers for repair or rebuilding, ensuring that only reliable equipment reached combat units. Training programs evolved to address the specialized requirements of flamethrower operations. The Chemical Warfare Service established schools at Army and Marine Corps installations, providing instruction in weapon maintenance, tactical employment, safety procedures, and combat techniques. Graduates of these schools formed cadres within combat units, training additional operators and maintaining institutional knowledge. The psychological aspects of flamethrower operations received increasing attention as American forces gained experience. Studies conducted by the Chemical Warfare Service's Medical Division examined the mental health effects on both operators and enemy personnel exposed to flame attacks. These investigations influenced training programs and operational procedures, emphasizing techniques for managing the stress associated with flame warfare. American flamethrower development also addressed safety concerns that had plagued earlier models. Improved fuel systems, better protective equipment, and enhanced training procedures reduced operator casualties from accidental ignition and fuel system failures. However, the fundamental dangers of carrying 70 pounds of flammable material remained unavoidable aspects of flame warfare. The M2's success influenced post-war American military doctrine and equipment development. Recognition of flamethrowers as essential infantry weapons led to their inclusion in standard tables of organization and equipment, ensuring that future forces would maintain organic flame capabilities. Technical innovations pioneered in the M2 program influenced development of other weapon systems, particularly in areas of ignition systems and fuel technology. International recognition of American flamethrower achievements led to extensive technology transfer programs. Allied nations requested technical assistance and equipment deliveries, while captured examples influenced enemy weapons development. The cartridge ignition system became the standard for post-war flamethrower design worldwide, testament to the engineering breakthrough achieved by the Chemical Warfare Service. The massive industrial complex at Schofield Barracks, Hawaii, bore little resemblance to a typical military installation in January 1944. What had begun as a small Chemical Warfare Service research facility now sprawled across 200 acres of converted warehouses, fabrication shops, and testing ranges. Under the direction of Colonel George Unmacked, this facility would produce more flame-throwing tanks than all American commercial manufacturers combined, revolutionizing both American industrial capacity and Pacific theater tactics. Colonel Unmack's transformation of Schofield Barracks into America's primary flame weapon production center began with a crisis. In November 1943, the Navy had delivered 5 Mark I flamethrowers to Hawaii for evaluation by Marine Corps units preparing for Operation Galvanic, the assault on Tarawa. Marine testing teams, led by Major James Roosevelt, declared the weapons unsuitable due to excessive weight and mechanical complexity. The Navy transferred the flamethrowers to Unmack's Chemical Warfare Service Detachment, creating an unexpected opportunity. Master machinists mate First Class Angelo Reich and electricians mate Second Class Joseph Kissel, both Navy CB specialists with extensive fabrication experience, examined the rejected Navy flamethrowers and recognized their potential for vehicle installation. Working 18-hour shifts in a converted aircraft hangar, they developed mounting systems that could adapt the Navy weapons to Sherman tank turrets while maintaining full traverse capability and armor protection. The first prototype, designated CB-H-14, Construction Battalion Hawaii Model 1, required 150 pounds of welding rod and over 1,100 electrical connections. Installation costs approached $25,000 per vehicle, equivalent to nearly $300,000 in modern currency, but the resulting capabilities justified the expense. Operating at 300 pounds per square inch pressure, the system achieved a 400-foot range with effective traverse of 270 degrees. Lieutenant Colonel Lewis Puller, visiting Schofield Barracks in December 1943, observed demonstrations of the CB-H-1 system and immediately requested flame tank support for his 1st Battalion, 7th Marines. His endorsement carried significant weight within Marine Corps leadership, leading to official requests for flame tank production. However, Unmack's facility lacked the industrial capacity to meet anticipated demand without major expansion. The solution came through cooperation with the Navy's construction battalions, whose CB units possessed both technical expertise and fabrication equipment. The 117th Naval Construction Battalion, scheduled for deployment to the Central Pacific, received orders to detach 25 specialists to Unmack's operation. These men brought welding equipment, machine tools, and years of experience converting standard equipment for specialized military applications. Chief Petty Officer Thomas Patterson, commanding the CB detachment, established production procedures that balanced quality control with manufacturing speed. Each flame tank conversion began with complete disassembly of the turret interior, followed by fabrication of custom mounting brackets and fuel system components. Electrical work required specialized training, as improper wiring could create fire hazards that would prove fatal in combat conditions. The production process for CB-H-1 installations demanded extraordinary precision and attention to detail. Fuel tanks, pressurization systems, and delivery mechanisms required exact specifications to achieve reliable operation under combat conditions. Any deviation from approved procedures could result in weapon failure during critical moments, potentially costing American lives and mission success. Quality assurance procedures, developed by Lieutenant Commander Robert Hayes of the Naval Material Laboratory, ensured that every installation met rigid specifications before acceptance. Each completed flame tank underwent 40 hours of testing, including range trials, pressure checks, and mechanical stress evaluations. Weapons that failed any aspect of testing returned to the production line for complete rebuilding. The first operational CB-H-1 flame tanks deployed with Marine forces preparing for Operation Forager, the assault on Saipan and Tinian in June 1944. 8 tanks, designated Satan by their crews, provided capabilities that transformed American assault tactics against Japanese fortifications. The psychological impact on Japanese defenders proved as significant as the physical destruction, with many positions abandoned upon approach of flame-equipped tanks. Colonel Harold Ames, commanding the 2nd Armored Amphibian Battalion during the Saipan operation, documented the tactical revolution created by flame tank availability. Japanese positions that had resisted infantry and artillery attacks for days were neutralized within minutes by flame tank employment. The mere appearance of flame-equipped Shermans often caused position abandonment before weapons were fired. Enemy morale collapsed completely in areas where flame attacks occurred. The success of CB-H-1 tanks prompted immediate expansion of production facilities at Schofield Barracks. Additional CB detachments, drawn from construction battalions throughout the Pacific, provided skilled personnel for accelerated production schedules. By September 1944, the facility employed over 300 specialists, working around-the-clock shifts to meet increasing demand from combat units. Industrial bottlenecks emerged as production expanded, particularly in specialized component manufacturing. Fuel tank fabrication required materials and techniques not readily available in forward areas, while pressurization systems demanded precision manufacturing beyond most field facilities. UNMAC's organization developed relationships with Australian and New Zealand manufacturers to supplement local production capacity. The Commonwealth Steelworks in Newcastle, Australia, under contract to the U.S. Army Chemical Warfare Service, produced fuel tanks and armor components for flame tank conversions. Australian manufacturing standards, developed for military applications, met American specifications while providing cost advantages and reduced shipping requirements. This international cooperation demonstrated the global industrial integration necessary for modern warfare. New Zealand's Hutt Railway Workshops, converted from locomotive manufacturing to military production, fabricated pressurization equipment and specialized tools for flame tank maintenance. The facility's experienced workforce, trained in precision mechanical work, adapted quickly to chemical warfare service requirements. Production schedules integrated New Zealand output with Hawaiian installation procedures, creating a supply chain spanning thousands of miles. Technological improvements continued throughout 1944 as combat experience revealed opportunities for enhancement. The CBH-2 system, introduced in October 1944, incorporated lessons learned from Saipan and Tinian operations. Improved nozzle design provided better flame characteristics, while enhanced fuel systems increased reliability under extreme conditions. The CBH-2's development process demonstrated the rapid innovation possible when industrial capacity combined with immediate combat feedback. Modifications identified by tank crews in forward areas could be incorporated into production within weeks, ensuring that technological improvements reached combat units with minimal delay. This responsiveness contrasted sharply with conventional military procurement procedures that required months or years for equipment modifications. Lieutenant James McBride, commanding a flame tank platoon during Tinian operations, provided detailed recommendations for system improvements based on 2 weeks of continuous combat employment. His suggestions, transmitted through official channels to Schofield Barracks, resulted in engineering changes that improved reliability by 15% and increased range by approximately 50 feet. These modifications were incorporated into production within 30 days of receipt. The industrial organization at Schofield Barracks evolved into a hybrid military-civilian enterprise that challenged traditional procurement and manufacturing procedures. Military personnel provided oversight and quality control, while civilian contractors and Navy Seabees handled actual production work. This arrangement maximized efficiency while maintaining accountability for critical military equipment. Financial management of the flame tank program required innovative approaches to traditional military contracting procedures. The urgency of wartime production demanded flexibility in procurement processes, while the specialized nature of flame tank conversion created unique cost accounting challenges. Colonel UNMAC's organization developed procedures that balanced fiscal responsibility with operational requirements. Cost per flame tank conversion stabilized at approximately $20,000 to $25,000, depending on specific system requirements and modification complexity. This figure included materials, labor, testing, and quality assurance procedures. While expensive compared to standard tank production, the combat effectiveness of flame-equipped vehicles justified the investment in terms of reduced casualties and accelerated mission accomplishment. Production scheduling became increasingly complex as demand expanded beyond original projections. Marine Corps requests for flame tank support grew from the original 8 vehicles for Saipan to 54 tanks for the Iwo Jima operation. Army requirements, initially minimal, increased dramatically as Pacific operations intensified. The 113th Tank Battalion, scheduled for Okinawa operations, requested conversion of their entire 54-tank complement to flame configuration. The CB workforce at Schofield Barracks demonstrated remarkable adaptability as production requirements evolved. Personnel originally trained in standard construction techniques mastered precision mechanical work, electrical systems, and specialized testing procedures. Cross-training programs ensured that production could continue despite personnel transfers and casualties, maintaining institutional knowledge within the organization. Training programs for flame tank crews paralleled production expansion, with specialized schools established to prepare operators and maintenance personnel. The Chemical Warfare Service developed curricula covering tactical employment, mechanical maintenance, safety procedures, and fuel handling techniques. These programs ensured that sophisticated equipment reached combat units with properly trained crews capable of maximizing its effectiveness. Technical documentation for flame tank operations required extensive development as systems became more complex and deployment expanded. Maintenance manuals, operating procedures, safety instructions, and troubleshooting guides were produced in multiple copies for distribution to combat units. This documentation proved essential for maintaining equipment reliability under field conditions where specialized technical support was unavailable. Supply chain management became critical as flame tank production expanded across multiple facilities and international suppliers. Raw materials, component parts, and specialized tools required coordination among American, Australian, and New Zealand sources. Transportation across thousands of miles of ocean, subject to enemy submarine attacks and weather delays, created logistical challenges that demanded careful planning and contingency procedures. Fuel production represented a parallel industrial effort that directly supported flame tank operations. Napalm manufacture required specialized facilities, trained personnel, and careful quality control to ensure consistent performance. The Chemical Warfare Service established production centers in Hawaii, Australia, and forward areas to minimize transportation requirements while maintaining adequate supplies for sustained operations. The Hawaiian Napalm Production Facility, established adjacent to the flame tank conversion operation at Schofield Barracks, could produce over 250,000 gallons of thickened fuel. This capacity exceeded the consumption requirements of all American flame operations in the Pacific Theater, providing strategic reserves for major operations. Quality control procedures ensured that fuel performance remained consistent across different production batches. Storage and handling of napalm required specialized facilities and trained personnel due to the material's flammable characteristics and chemical properties. Underground storage tanks, equipped with fire suppression systems and safety monitoring equipment, protected fuel supplies from enemy action and accidental ignition. Personnel training emphasized safety procedures and emergency response techniques to minimize risks associated with large-scale fuel operations. Transportation of completed flame tanks to combat zones created unique logistical requirements. The modified vehicles, with their specialized fuel systems and pressurization equipment, required careful handling during shipment to prevent damage. Loading procedures, developed specifically for flame-equipped tanks, ensured that weapons arrived in combat areas ready for immediate employment. The industrial success at Schofield Barracks influenced American defense procurement policies and demonstrated the potential of hybrid military-civilian manufacturing arrangements. The flexibility and innovation achieved under wartime conditions provided lessons for peacetime defense production, particularly in areas requiring rapid technological development and deployment. International cooperation in flame weapon production established precedents for post-war alliance relationships and technology sharing agreements. The successful integration of American design requirements with Australian and New Zealand manufacturing capabilities demonstrated possibilities for multinational defense production that would influence Cold War military planning. The volcanic sand of Iwo Jima's beaches absorbed the morning rain on February 19, 1945, as 70,000 Marines prepared for the largest amphibious assault in Pacific War history. Among the invasion fleet's cargo holds, 8 CB-H-2 flame tanks and dozens of M2 portable flamethrowers represented the culmination of 4 years of American flamethrower development. What would unfold over the next 36 days would prove these weapons indispensable for victory while revealing the terrible human cost of cave warfare. First Lieutenant Harold Schreier of Company E, 2nd Battalion, 28th Marines, carried serial number 47893 M2 flamethrower as his rifle company approached the base of Mount Suribachi. The weapon, manufactured at the Ronson Corporation's Newark, New Jersey facility in January 1945, had arrived at Iwo Jima with perfect maintenance records and 100% ignition reliability during pre-invasion testing. Schreier's flame team included Private First Class Theodore White as assistant operator and Corporal Michael Petrosky providing rifle protection. The Japanese defensive positions on Iwo Jima represented the ultimate test for American flamethrower technology. General Tadamaki Kurabayashi had spent 8 months creating a labyrinth of caves, tunnels, and reinforced bunkers connected by 11 miles of underground passages. Traditional weapons artillery, naval gunfire, and conventional explosives had proven inadequate during 3 days of preliminary bombardment. Only weapons capable of reaching into the deepest caves could dislodge Japanese defenders. Lieutenant Schreier's first employment of the M2 occurred at 8:45 on D-Day morning against a concealed machine gun position 30 meters inland from Red Beach 1. The Japanese gunners, positioned in a reinforced concrete bunker with a single firing embrasure, had pinned down 2 rifle squads for over an hour. Artillery fire and rocket attacks had failed to neutralize the position, leaving infantry assault as the only apparent option. Approaching under covering fire from Browning automatic rifles, Schreier's flame team reached effective range without casualties despite concentrated enemy fire. The M2's cartridge ignition system functioned flawlessly, sending a 40-meter stream of napalm through the bunker embrasure and into the defensive position beyond. Japanese resistance ceased immediately, allowing infantry to advance and secure the objective within minutes. The psychological effect was incredible, Schreier reported in his after-action statement. Japanese defenders who had shown no fear of artillery or rifle fire abandoned positions immediately upon witnessing flame attacks. Word spread quickly among enemy units, causing premature abandonment of positions that hadn't even been attacked. Technical Sergeant Woody Williams of Company C, 1st Battalion, 21st Marines, 3rd Marine Division, arrived on Iwo Jima's beaches on D+3 with 4 years of flamethrower experience across multiple Pacific campaigns. His M2, serial number 52174, had been personally modified with improved sight brackets and enhanced grip surfaces based on combat lessons from Bougainville and Guam. Williams would earn the Medal of Honor for his February 23 actions, demonstrating the tactical impact possible with expertly operated flame weapons. Williams' most significant engagement occurred near Hill 382, where Japanese defenders had constructed a complex of 7 interconnected bunkers covering the only practical approach route for American armor. Previous attacks by 2 rifle companies, supported by artillery and close air support, had failed with heavy casualties. Marine commanders estimated that conventional assault would require at least battalion-strength forces and accept extremely high casualty rates. The flame attack, conducted by Williams with minimal infantry support, neutralized all 7 positions within 2 hours. His tactical approach demonstrated the evolution of American flamethrower employment from crude assault techniques to sophisticated combined arms procedures. Each bunker attack involved preliminary reconnaissance, coordinated covering fire, concealed approach movement, and precise flame application followed by immediate infantry occupation. The key was understanding that the flamethrower wasn't just about killing enemy soldiers, Williams explained in post-war interviews. It was about forcing them to abandon positions they couldn't be driven from any other way. Once they left their caves and bunkers, conventional weapons could deal with them effectively. The CBH-2 flame tanks, designated Mark I by Marine crews, provided capabilities impossible with portable weapons. Sergeant Joseph Kissel, the Navy CB specialist who had designed the system, accompanied the flame tanks to Iwo Jima to oversee maintenance and troubleshooting. His presence proved essential as combat conditions revealed previously unknown stress factors that affected system performance. Tank Commander Staff Sergeant Robert Rodriguez of the 4th Tank Battalion reported typical CB-H2 employment during the assault on Japanese positions near the quarry. We could engage enemy caves from ranges where their anti-tank weapons couldn't reach us effectively. The 400-foot range let us stay behind cover while directing flame streams into cave mouths and bunker openings. Japanese defenders either died in the flames or abandoned positions to escape the fire. The flame tank's psychological impact extended far beyond their direct targets. Japanese commanders, recognizing the threat posed by vehicle-mounted flamethrowers, concentrated anti-tank weapons and artillery fire against flame-equipped Shermans. This defensive reaction drew enemy fire away from conventional tanks and infantry, providing tactical advantages that complemented the direct effects of flame attacks. However, the intensity of Japanese resistance on Iwo Jima revealed limitations in American flamethrower tactics and equipment. Enemy forces, fighting for homeland territory with no possibility of evacuation, demonstrated determination that exceeded anything previously encountered. Japanese defenders often remained in position despite flame attacks, accepting death rather than abandoning their posts. Private First Class Charles Lindbergh of Company F, 2nd Battalion, 27th Marines, documented the failure of psychological warfare aspects during his unit's assault on Nishi Ridge. The Japanese soldiers in those caves knew they were going to die anyway. The flamethrower attacks killed them, but didn't make them surrender or run away like they did on other islands. We had to burn out every position individually, which took much longer and used much more fuel than we'd expected. Fuel consumption on Iwo Jima exceeded all planning projections, creating logistical challenges that threatened continued flame operations. The CBH-2 tanks consumed between 5,000 and 10,000 gallons of napalm daily during periods of intensive fighting. Portable flamethrowers, with their 7-second fuel capacity, required constant resupply to maintain operational effectiveness. Supply units struggled to maintain adequate fuel stocks under these consumption rates. The 133rd Naval Construction Battalion, responsible for establishing fuel storage and distribution facilities on Iwo Jima, worked under constant enemy fire to create infrastructure supporting flame operations. CB personnel constructed underground fuel storage tanks, distribution pipelines, and refueling stations within artillery range of Japanese positions. Their efforts ensured that flame weapons remained supplied throughout the 36-day battle. Casualty rates among flamethrower operators on Iwo Jima demonstrated the extreme dangers associated with flame warfare. The portable flame units of 1 Marine Battalion suffered 92% casualties during the first 2 weeks of fighting. Operators, easily identified by their distinctive equipment and tactical importance, became priority targets for Japanese marksmen and anti-tank weapons. Corporal Raymond Hart of Company E, 2nd Battalion, 28th Marines, survived multiple flame missions on Iwo Jima despite being wounded twice by Japanese sniper fire. His helmet, perforated by a bullet that creased his temple, illustrated the targeting that flamethrower operators faced throughout the campaign. Hart's survival and continued combat effectiveness demonstrated the importance of proper training and tactical procedures for flame weapon employment. The tactical evolution of flamethrower operations during the Iwo Jima campaign reflected American adaptability under extreme combat conditions. Initial employment methods, based on experience from earlier Pacific operations, proved inadequate against the sophisticated defensive positions constructed by Japanese forces. New techniques, developed through trial and error under fire, became standard procedures for subsequent operations. Marine Corps innovation in corkscrew and blowtorch tactics combined multiple weapon systems to maximize effectiveness while minimizing casualties. Browning automatic rifle teams provided suppressing fire to keep Japanese defenders underground, while flamethrower operators approached target positions under this protective umbrella. Demolition teams followed flame attacks to permanently destroy positions and prevent reoccupation. The integration of flame tanks with infantry assault teams required new coordination procedures and communication techniques. Tank-infantry cooperation, already complex under normal conditions, became even more challenging when flame weapons were involved. Friendly fire incidents, caused by inadequate coordination between tank crews and infantry units, highlighted the need for improved training and standardized procedures. First Lieutenant John Keith, commanding a flame tank section during the assault on Hill 362, developed procedures that became standard throughout the Pacific Theater. We established contact with infantry units before beginning any flame attack. The infantry would mark target locations with smoke grenades and withdraw to safe distances. Only after confirming friendly troop locations would we begin flame operations. This prevented casualties from our own weapons. Japanese countermeasures against American flame weapons evolved throughout the Iwo Jima campaign as enemy forces gained experience with American tactics and equipment. Initial Japanese responses, based on experience from earlier Pacific battles, proved inadequate against the improved American weapons and more sophisticated employment methods. Enemy adaptations forced corresponding American tactical modifications. Colonel Takechi Nishi, commanding Japanese tank units on Iwo Jima, developed techniques for neutralizing American flame tanks through coordinated anti-tank gun and artillery fire. His forces concentrated multiple weapons against individual flame tanks, recognizing their tactical importance and vulnerability to concentrated fire. Japanese success in destroying several CB-H-2 tanks forced American commanders to modify employment procedures and provide additional protection. Japanese defensive innovations included constructing positions specifically designed to counter flame attacks. Cave entrances were modified with multiple turns and baffles to prevent flame penetration, while ventilation systems were designed to exhaust flame-heated air and gases. Some positions incorporated water systems that could flood firing chambers to extinguish flame attacks. Private First Class Kuniaka Yamada of the 109th Infantry Battalion provided detailed accounts of Japanese defensive procedures during his post-capture interrogation. "We knew the American flame weapons were coming, so we prepared our positions to survive flame attacks. Multiple chambers and escape routes meant that defenders could retreat from flame-attacked areas and return after the attack ended. Some positions had stone barriers that blocked flame streams while allowing return fire through small openings. The technical performance of American flamethrowers on Iwo Jima validated design decisions made during the development process while revealing areas for further improvement. The M2's cartridge ignition system achieved reliability rates exceeding 95% despite extreme combat conditions, saltwater exposure, and rough handling. The napalm fuel mixture provided effective range and adherence characteristics that maximized tactical impact. However, combat experience revealed mechanical stress factors that had not been anticipated during testing. The M2's valve systems and pressure regulators required more frequent maintenance than projected, while the harsh conditions on Iwo Jima accelerated wear on moving parts. Chemical Warfare Service technical representatives, attached to combat units, provided field maintenance expertise and collected performance data for future improvements. Staff Sergeant Anthony D'Amato, a chemical warfare service technician supporting the 5th Marine Division, documented maintenance requirements for M2 flamethrowers under combat conditions. The volcanic sand got into everything, causing valve problems and ignition failures. We had to strip and clean weapons every day to maintain reliability. Saltwater corrosion was also a major problem, especially for weapons that had been submerged during beach landings. The CB-H-2 flame tanks demonstrated exceptional mechanical reliability despite the challenging operating environment. Navy CB specialists, integrated with Marine tank crews, provided maintenance expertise that kept the complex systems operational throughout extended combat operations. The cooperation between Navy technical personnel and Marine combat crews illustrated effective inter-service coordination under extreme conditions. Fuel quality control became critical for maintaining weapon performance as combat operations continued. Napalm stored under field conditions was subject to contamination, separation, and chemical degradation that could affect flame characteristics. Quality assurance procedures, developed specifically for combat conditions, ensured that fuel performance remained consistent despite storage and handling challenges. The strategic impact of flamethrower operations on Iwo Jima extended beyond immediate tactical results. The effectiveness of American flame weapons, documented in detailed after-action reports and confirmed by prisoner interrogations, influenced Japanese defensive planning for subsequent operations. Enemy forces began modifying defensive positions and tactics specifically to counter expected American flame attacks. Intelligence reports from the Okinawa campaign, beginning in April 1945, confirmed that Japanese forces had incorporated anti-flame defensive measures throughout their fortified positions. Cave systems included water barriers, ventilation modifications, and structural changes designed to reduce vulnerability to flame attacks. These modifications represented direct responses to American flame weapon effectiveness demonstrated on Iwo Jima. The human cost of flame warfare, clearly demonstrated during the Iwo Jima campaign, influenced American tactical doctrine and equipment development for subsequent operations. The 92% casualty rate among portable flame operators forced reconsideration of employment methods and led to increased emphasis on vehicle-mounted systems that provided better crew protection. Medical treatment of flame weapon casualties required specialized procedures and equipment not readily available in forward areas. Burns from napalm, both on American operators and Japanese defenders, presented unique challenges for medical personnel. Treatment protocols developed during the campaign became standard procedures for Pacific Theater medical units. The psychological impact of flame warfare on American personnel also required consideration. Many Marines reported difficulty sleeping and recurring nightmares following flame operations. The intimate nature of flame warfare, requiring close approach to enemy positions and direct observation of flame effects, created psychological stresses different from conventional combat. Post-battle analysis of Iwo Jima operations confirmed that American flamethrower development had achieved its primary objectives. The M2 portable flamethrower and CBH-2 flame tanks provided capabilities that conventional weapons could not match for reducing fortified positions. However, the terrible cost in human lives and the limited tactical applications made flame weapons tools of last resort rather than primary assault weapons. The morning mist lifted from Okinawa's coral ridges on April 1, 1945, revealing the largest amphibious force ever assembled in the Pacific War. Hidden among the conventional Sherman tanks of the 713th Tank Battalion were 54 flame-equipped vehicles that would determine the outcome of 3 months of brutal fighting. These Ronson flame tanks, converted at Schofield Barracks and designated POA CWS H-1 by Army Chemical Corps nomenclature, represented the ultimate evolution of American flame warfare technology. Colonel Harry Knight, commanding the 713th Tank Battalion, had overseen the conversion of his entire unit from conventional armor to flame configuration during 3 months of intensive training at Schofield Barracks. The decision to commit an entire tank battalion to flame warfare reflected lessons learned from Iwo Jima, where the limited number of flame tanks had created tactical bottlenecks that prolonged operations and increased casualties. The Ronson flame tanks, though less capable than the CBH-1 and CBH-2 systems used by Marines, provided advantages in reliability and maintenance simplicity that proved essential for sustained operations. Operating at lower pressures than the Navy design systems, the Ronson equipment achieved ranges of approximately 150 feet while consuming less fuel per engagement. This efficiency would prove critical during the prolonged Okinawa campaign. Technical Sergeant James Murphy, a tank commander in Company B of the 713th Battalion, had participated in the conversion process and understood the technical differences between flame tank variants. The Ronson system was simpler than the Marine flame tanks we'd seen on Iwo Jima. Lower pressure meant less range, but also fewer mechanical problems and easier maintenance. For a sustained operation like Okinawa, reliability mattered more than maximum performance. The Japanese defensive system on Okinawa represented the culmination of 4 years of defensive warfare experience. Lieutenant General Mitsuru Ushijima had constructed 3 successive defensive lines incorporating every lesson learned from previous Pacific battles. The Shuri Line, anchored on ancient fortifications and limestone caves, was designed specifically to counter American flame tactics while maximizing Japanese defensive advantages. General Ushijima's defensive preparations included specific countermeasures against American flame weapons. Japanese engineers had modified cave systems with baffles, water barriers, and ventilation systems designed to defeat flame penetration. Anti-tank guns were positioned to cover approaches to critical defensive positions, while artillery observers were trained to direct concentrated fire against flame-equipped vehicles. The scale of Japanese defensive preparations became apparent during the first major American assault on April 19, 1945. 3 divisions of the 24th Corps attacked positions that had withstood 5 days of artillery preparation and naval bombardment. Conventional weapons, including the heaviest artillery concentrations of the Pacific War, had failed to reduce Japanese defensive strength significantly. Lieutenant Colonel Edwin May, commanding the 2nd Battalion, 96th Infantry Division, requested flame tank support after his conventional attacks failed with heavy casualties. We'd been hitting these positions for 18 hours with everything we had: artillery, mortars, bazookas, even close air support. The Japanese kept fighting from caves and bunkers that our weapons couldn't reach. When the flame tanks arrived, positions that had held up entire companies were neutralized within minutes. The tactical employment of flame tanks on Okinawa required coordination between Army and Marine Corps units that had developed different doctrines and procedures. The 713th Tank Battalion supported both Army infantry divisions and Marine combat units, necessitating flexible procedures that could accommodate varying tactical requirements and communication systems. Captain Robert Patterson, serving as liaison officer between the 713th Tank Battalion and Marine units, developed coordination procedures that became standard for inter-service flame operations. The key was establishing common communication frequencies and standardized target designation methods. Marines and Army infantry used different procedures, so we had to create systems that worked for everyone. Training exercises before the battle made all the difference. The intensity of fighting on Okinawa created fuel consumption rates that exceeded all previous projections. Flame tanks consumed over 200,000 gallons of napalm during 3 months of operations, requiring continuous resupply operations under enemy fire. The 43rd Chemical Laboratory Company, responsible for fuel production and distribution, worked around the clock to maintain adequate supplies. Supply operations for flame warfare required specialized equipment and procedures that conventional logistical units were not equipped to handle. Fuel trucks, storage facilities, and distribution systems had to be protected from enemy artillery and air attacks while remaining accessible to forward combat units. The vulnerability of fuel supplies to enemy action created tactical constraints that influenced operational planning. First Lieutenant Charles Anderson, commanding a fuel supply platoon supporting flame operations, documented the challenges of maintaining fuel stocks under combat conditions. Japanese artillery targeted our fuel dumps whenever they could identify their locations. We had to disperse supplies and use underground storage to prevent catastrophic losses. Moving fuel forward to the flame tanks required careful timing and route selection to avoid enemy observation. The effectiveness of American flame weapons on Okinawa varied significantly depending on terrain conditions and Japanese defensive preparations. Positions constructed specifically to counter flame attacks proved more resistant than earlier Pacific Theater fortifications, requiring multiple flame applications or combination with other weapon systems to achieve neutralization. Staff Sergeant Michael Romano, a flame tank operator with extensive combat experience, observed the evolution of Japanese defensive techniques. The Japanese had learned from our earlier operations and modified their positions accordingly. Cave entrances were designed to deflect flame streams, and some positions had water systems that could extinguish our attacks. We had to adapt our tactics constantly to counter their improvements. Japanese countermeasures against American flame tanks became increasingly sophisticated as the Okinawa campaign progressed. Enemy forces developed techniques for destroying flame-equipped vehicles through coordinated attacks by multiple anti-tank weapons, artillery concentrations, and suicide assault teams equipped with satchel charges and magnetic mines. The vulnerability of flame tanks to Japanese anti-tank tactics became apparent during fighting for the Shuri Line in May 1945. Several 713th Battalion tanks were destroyed by coordinated enemy action, forcing modifications to tactical employment procedures and additional protective measures for flame-equipped vehicles. Captain Thomas Rodriguez, commanding Company C of the 713th Tank Battalion, developed new tactics to counter Japanese anti-tank efforts. We started using conventional tanks to suppress enemy anti-tank positions before bringing up the flame tanks. Infantry support became even more critical to protect against Japanese assault teams. The coordination required was complex, but it reduced our losses significantly. The battle for Kakazu Ridge demonstrated both the potential and limitations of flame tank operations against prepared Japanese defenses. American forces, supported by intensive artillery preparation and close air support, had failed to reduce Japanese positions during 3 days of continuous attacks. The introduction of flame tanks changed the tactical situation dramatically but also revealed the costs associated with flame warfare. Major William Thompson, commanding the 1st Battalion, 383rd Infantry, requested flame tank support after conventional methods proved inadequate. Japanese positions were built into limestone caves that artillery couldn't touch. Our infantry was taking heavy casualties trying to assault prepared positions. The flame tanks gave us capabilities we needed, but the fighting was still brutal. The flame tank attack on Kakazu Ridge, conducted by elements of the 713th Tank Battalion, neutralized Japanese defensive positions but required coordinated support from artillery, infantry, and combat engineers. The complexity of the operation illustrated how flame warfare had evolved from simple weapon employment to sophisticated combined arms procedures requiring extensive planning and coordination. Technical innovations continued throughout the Okinawa campaign as combat experience revealed opportunities for improvement. Field modifications to flame tank systems, developed by unit maintenance personnel and chemical warfare service technical representatives, improved reliability and effectiveness under combat conditions. Sergeant First Class Joseph Kowalski, Chief Mechanic for Company A of the 713th Tank Battalion, developed field expedient repairs that kept flame systems operational despite parts shortages and combat damage. We couldn't wait for replacement parts, so we learned to fabricate what we needed from salvaged materials. The fuel systems were the most critical components, and we developed ways to repair pressure lines and valves using whatever was available. The prolonged nature of the Okinawa campaign created maintenance challenges that had not been encountered during shorter Pacific operations. Flame tank systems, operating under continuous combat conditions for 3 months, required more extensive maintenance than anticipated during peacetime testing, where patterns and failure modes identified during Okinawa operations influenced post-war equipment design. The psychological effects of sustained flame warfare became apparent during the Okinawa campaign as both American and Japanese personnel were exposed to flame combat for extended periods. American flame tank crews reported stress-related problems including nightmares, difficulty sleeping, and reluctance to participate in flame operations after witnessing their effects on enemy personnel. Combat medics attached to flame tank units developed specialized procedures for treating psychological casualties related to flame warfare. The intimate nature of flame combat, requiring operators to observe the direct effects of their weapons on enemy personnel, created stress patterns different from conventional armored warfare. Captain David Miller, a medical officer supporting the 713th Tank Battalion, documented psychological effects of flame warfare on American personnel. Tank crews who operated flame systems showed higher rates of stress-related symptoms than conventional tank operators. The visual impact of flame weapons created psychological pressures that we hadn't anticipated. Rotation policies and counseling programs helped manage these problems. Japanese defensive tactics evolved throughout the Okinawa campaign as enemy forces developed techniques for countering American flame weapons. Intelligence reports indicated that Japanese commanders had studied American flame tactics from previous operations and developed specific countermeasures designed to minimize flame weapon effectiveness. Captured Japanese documents revealed detailed analysis of American flame tank capabilities and limitations. Enemy intelligence had identified mechanical vulnerabilities, tactical employment patterns, and logistical requirements that could be exploited to reduce flame weapon effectiveness. This intelligence prompted modifications to Japanese defensive positions and tactics. Colonel Hiromichi Yahara, Chief of Staff for Japanese forces on Okinawa, provided detailed accounts of Japanese anti-flame preparations during post-war interrogations. We studied American flame tactics from Iwo Jima and other battles. Our engineers designed cave systems specifically to defeat flame penetration, and our artillery was trained to concentrate fire on flame tanks. We understood that these weapons were critical to American success. The effectiveness of Japanese countermeasures varied significantly depending on terrain conditions and available resources. Positions constructed with adequate time and materials proved more resistant to flame attacks, while hastily prepared defenses remained vulnerable. The quality of Japanese defensive preparations became a critical factor determining American casualty rates and operational tempo. American tactical adaptations to counter Japanese anti-flame measures included increased use of conventional supporting arms, modified approach routes, and improved coordination between flame units and conventional forces. These adaptations demonstrated American flexibility and tactical innovation under combat conditions. The integration of flame tanks with conventional armor and infantry became increasingly sophisticated as the Okinawa campaign progressed. Combined arms procedures, developed through combat experience, maximized the effectiveness of specialized flame capabilities while minimizing vulnerabilities to enemy countermeasures. Lieutenant Colonel Robert Hayes, commanding the 1st Battalion, 7th Marines, developed procedures for integrating flame tanks with marine infantry that became standard throughout the Pacific theater. Flame tanks couldn't operate alone against prepared positions. They needed conventional tanks for protection, artillery for suppression, and infantry for close support. When all these elements worked together, we could reduce Japanese positions that nothing else could touch. The logistical requirements for sustained flame operations on Okinawa demonstrated the industrial capacity necessary to support advanced military technology under combat conditions. Fuel production, equipment maintenance, and personnel training required resources that exceeded the capabilities of forward-deployed forces. The success of American flame operations on Okinawa depended on industrial support systems extending from combat zones back to manufacturing facilities in the continental United States. This integration of battlefield requirements with industrial production capabilities illustrated the total warfare concepts that determine victory in modern conflicts. Supply chain management for flame operations required coordination among multiple agencies and services. The Chemical Warfare Service provided technical expertise and specialized equipment, while conventional supply organizations handled transportation and storage. Navy CB units provided maintenance and repair capabilities that kept complex systems operational under field conditions. The strategic impact of flame operations on Okinawa extended beyond immediate tactical results. The effectiveness of American flame weapons influenced Japanese planning for homeland defense operations and contributed to decisions regarding continued resistance versus surrender negotiations. Intelligence assessments indicated that Japanese commanders recognized the tactical advantages provided by American flame weapons and understood that similar capabilities would be decisive during any invasion of the Japanese home islands. This recognition contributed to Japanese willingness to consider surrender negotiations rather than continue resistance that could not prevent ultimate defeat. The human cost of flame warfare on Okinawa, while significant, was substantially lower than equivalent operations using conventional weapons. The ability of flame weapons to force abandonment of defensive positions reduced the casualties associated with direct infantry assault while minimizing damage to critical infrastructure. The Okinawa campaign demonstrated that American flamethrower development had achieved its primary objectives of providing capabilities for reducing fortified positions that conventional weapons could not neutralize effectively. The technical reliability, tactical effectiveness, and logistical sustainability of American flame systems proved superior to enemy capabilities and contributed significantly to operational success. However, the extreme conditions of the Okinawa fighting also revealed limitations in flame warfare that influenced post-war military planning. The specialized nature of flame operations, high personnel training requirements, and significant logistical demands made flame weapons suitable for specific tactical situations rather than general infantry employment. The research laboratories at the Massachusetts Institute of Technology buzzed with activity throughout the summer of 1943 as Dr. Louis Fieser's team conducted the final tests on their revolutionary fuel-thickening compound. Napalm, derived from the aluminum naphthenate and aluminum palmitate soaps that gave the substance its name, would transform flamethrower warfare by solving the fundamental limitations that had plagued every previous flame fuel composition. Traditional flamethrower fuels, based on gasoline or oil mixtures, dispersed rapidly after leaving the weapon's nozzle, creating brief flame bursts with limited range and minimal adhesion to targets. Dr. Fieser's aluminum soap compound created a gel-like consistency that maintained cohesion during flight, dramatically extending effective range while enabling the fuel to stick to surfaces and continue burning for extended periods. The development process for napalm began with Dr. Fieser's analysis of captured German flame fuels, which included tar additives designed to improve burning characteristics and surface adhesion. Working under contract to the Office of Scientific Research and Development, his team experimented with various thickening agents before discovering that aluminum soaps provided optimal characteristics for military applications. Laboratory testing at MIT demonstrated that napalm-thickened fuel achieved ranges of 40 to 60 meters, compared to 15 to 20 meters for conventional gasoline mixtures. The improved fuel burned at temperatures exceeding 2,190 degrees Fahrenheit while adhering to surfaces for several minutes after initial contact. These characteristics revolutionized the tactical effectiveness of flame weapons. Captain Robert Patterson of the Chemical Warfare Service's Technical Division observed early napalm demonstrations and immediately recognized the implications for American flamethrower development. The thickened fuel solved every major problem we'd encountered with conventional flame weapons. Range increased dramatically, the flame stream remained coherent over longer distances, and the fuel continued burning after impact. This was the breakthrough we'd been searching for. However, existing American flamethrowers could not effectively utilize napalm due to inadequate pressure systems and fuel delivery mechanisms designed for conventional gasoline. The M1 flamethrower's operating pressure of 40 pounds per square inch proved insufficient to project thickened fuel effectively, while the weapon's fuel system components were unable to handle the increased viscosity of napalm mixtures. The development of the M1A1 flamethrower represented American efforts to adapt existing equipment for napalm employment while maintaining production continuity. Modifications included upgraded pressure systems, revised fuel delivery components, and strengthened structural elements designed to handle the increased operating pressures required for thickened fuel projection. Testing of the M1A1 at Dugway Proving Ground in Utah during fall 1943 demonstrated significant performance improvements over the original M1 design. Range increased to 45 meters consistently, while flame duration and surface adhesion characteristics provided tactical advantages impossible with conventional fuels. However, the weapon retained the problematic hydrogen ignition system that limited reliability under combat conditions. Lieutenant Colonel William Porter, commanding the Chemical Warfare Services Research and Development Division, recognized that revolutionary fuel technology required equally revolutionary ignition systems to achieve maximum effectiveness. His analysis of German Flammenwerfer 41 weapons captured in North Africa revealed cartridge ignition systems that offered superior reliability compared to American electrical designs. The cartridge ignition concept utilized small pyrotechnic charges similar to signal flare components to provide instantaneous ignition regardless of weather conditions or mechanical shock. Unlike electrical systems that required batteries, wiring, and complex electronic components, cartridge ignition used simple mechanical principles that were inherently more reliable under combat conditions. American development of cartridge ignition systems began at the Frankfurt Arsenal in Pennsylvania, where ordnance specialists possessed extensive experience with pyrotechnic devices and mechanical firing mechanisms. The design team, led by Major George Smith, adapted existing signal flare technology to create ignition cartridges specifically optimized for flamethrower applications. The resulting ignition cartridge measured approximately 2 inches in length and contained a precise mixture of chemicals designed to produce sustained ignition temperatures for several seconds. The cartridges were loaded into a revolver-like cylinder that advanced automatically with each weapon firing, providing multiple ignition attempts without operator intervention during combat operations. Testing of cartridge ignition systems at Aberdeen Proving Ground demonstrated reliability rates exceeding 98% across diverse environmental conditions including extreme cold, high humidity, salt water immersion, and mechanical shock equivalent to combat handling. This performance represented a dramatic improvement over electrical systems that failed in approximately 40% of combat employment attempts. The integration of napalm fuel technology with cartridge ignition systems created the technical foundation for the M2 flamethrower, representing a quantum leap in American flame weapon capabilities. The new weapon combined the range and effectiveness advantages of thickened fuel with the reliability benefits of pyrotechnic ignition, producing a system that performed consistently under the most demanding combat conditions. Production engineering for the M2 flamethrower required collaboration among multiple manufacturers with specialized capabilities in different component areas. The Ronson Corporation, famous for cigarette lighters, provided expertise in ignition systems and flame control mechanisms. Liquid Carbonic Corporation contributed pressurization technology developed for industrial gas applications. Dozens of smaller contractors produced specialized components under Chemical Warfare Service coordination. Quality control procedures for M2 production established standards that exceeded those for most military equipment due to the critical nature of ignition system reliability. Each weapon underwent extensive testing including ignition reliability trials, pressure system verification, fuel delivery performance checks, and complete system integration evaluation. Weapons that failed any aspect of testing were completely rebuilt rather than repaired. The M2's fuel system design incorporated lessons learned from earlier flamethrower development while optimizing performance for napalm employment. Fuel tanks, constructed from lightweight aluminum alloy, provided corrosion resistance and reduced overall weapon weight. Pressure regulators maintained consistent operating pressure throughout the fuel load, ensuring uniform range and flame characteristics from first shot to fuel exhaustion. The ignition system represented the most innovative aspect of M2 design, incorporating multiple safety features and backup capabilities that prevented accidental discharge while ensuring reliable combat performance. The cartridge magazine held sufficient ignition rounds for extended operations, while the firing mechanism was designed to function even after severe mechanical damage or environmental exposure. Field maintenance procedures for the M2 were simplified compared to earlier models, reflecting design emphasis on combat reliability rather than manufacturing cost reduction. Operators could perform most routine maintenance tasks using standard infantry equipment, while major repairs required specialized tools and training available at unit level rather than requiring factory return. Training programs for M2 operations emphasized both technical proficiency and tactical employment techniques developed through extensive combat experience. The Chemical Warfare Service established training facilities at military installations worldwide, providing standardized instruction that ensured consistent performance regardless of unit assignment or geographical location. The development of vehicle-mounted flamethrower systems represented parallel technical evolution that complemented portable weapon capabilities while providing advantages impossible with man-carried equipment. Tank-mounted flame systems could achieve ranges exceeding 400 feet, while providing armor protection for operators and carrying fuel loads sufficient for sustained operations. The CB-H-1 and CB-H-2 flame tanks, developed by Navy CB specialists at Schofield Barracks, incorporated napalm technology and cartridge ignition principles in vehicle-mounted configurations optimized for Pacific theater operations. These systems operated at pressures of 300 pounds per square inch, far exceeding the capabilities of portable weapons, while maintaining reliability standards necessary for combat employment. Technical innovations in fuel production and quality control ensured that napalm performance remained consistent across different manufacturing facilities and geographic locations. The Chemical Warfare Service established production standards that controlled fuel composition, thickening agent concentration, and chemical additives to maintain uniform burning characteristics and tactical effectiveness. Storage and transportation of napalm required specialized procedures due to the material's flammable nature and chemical characteristics. Underground storage facilities, equipped with fire suppression systems and environmental controls, protected fuel supplies from enemy action and accidental ignition while maintaining chemical stability over extended periods. The integration of flamethrower technology with other weapon systems created combined arms capabilities that exceeded the sum of individual component effectiveness. Flame weapons could neutralize targets immune to conventional firearms, while conventional weapons provided protection for flame operators during approach and engagement phases. Communication systems for coordinating flame operations required specialized procedures that accounted for the unique characteristics of flame warfare. Radio protocols, visual signals, and coordination techniques were developed specifically for flame operations to ensure effective integration with supporting arms while minimizing friendly fire incidents. Medical treatment capabilities for flame warfare casualties required specialized equipment and procedures not available through conventional military medical systems. Treatment protocols for napalm burns, both on friendly personnel and enemy casualties, were developed based on combat experience and laboratory research into burn physiology and treatment methods. Psychological warfare aspects of flame weapons received extensive study as American forces gained experience with their terror effects on enemy personnel. Research conducted by the Chemical Warfare Service's Medical Division examined the mental impact of flame weapons on both operators and enemy personnel exposed to flame attacks, influencing tactical employment procedures and training programs. Environmental effects of napalm employment became apparent during extended combat operations in tropical climates. The persistence of burning napalm created fire hazards that could spread beyond intended targets, while chemical residues from burnt fuel affected local ecosystems and water supplies. These environmental considerations influenced operational planning and post-combat cleanup procedures. International law implications of flame weapon employment required careful consideration as American forces expanded their use of these weapons. Legal analysis conducted by military lawyers examined the Geneva Convention provisions regarding incendiary weapons while developing employment guidelines that remained within accepted international standards. Intelligence collection regarding enemy flame weapon capabilities required specialized technical analysis to assess foreign developments and countermeasures. Captured enemy equipment was subjected to detailed examination to understand technological approaches, performance characteristics, and potential improvements that could influence American development programs. Research and development priorities for future flame weapon improvements were established based on combat experience and technological possibilities. Areas of focus included increased range capabilities, improved fuel efficiency, reduced weapon weight, and enhanced reliability under extreme environmental conditions. The technical revolution in American flamethrower development demonstrated the importance of integrating multiple technological innovations to achieve dramatic performance improvements. The combination of napalm fuel technology, cartridge ignition systems, improved manufacturing techniques, and sophisticated employment procedures created capabilities that transformed infantry tactics and operational planning. This technological integration also illustrated the relationship between scientific research, industrial production, and military requirements in modern warfare. The success of American flame weapons resulted from coordinated efforts among university researchers, commercial manufacturers, and military organizations working toward common objectives under wartime conditions. The morning of May 8, 1945, brought silence to European battlefields for the first time in 6 years. But the lessons of flamethrower warfare continued to resonate through military planning organizations worldwide. Intelligence reports from captured German facilities revealed that Axis powers had studied American flame weapon developments intensively, while Allied nations sought to understand and replicate the technological advantages that had proven so decisive in Pacific theater operations. British War Office analysts, examining captured German documentation from the Kummersdorf research facility, discovered extensive intelligence gathering efforts focused on American M2 flamethrower capabilities. German engineers had analyzed weapon fragments recovered from various battlefields, attempting to reverse engineer the cartridge ignition system and napalm fuel technology that had revolutionized flame warfare effectiveness. Major General John Barnes, commanding British Chemical Defense Experimental Establishment at Porton Down, submitted a comprehensive assessment of American flamethrower achievements to the Imperial General Staff in June 1945. American developments in portable flame weapons represent the most significant advance in infantry assault capabilities since the introduction of automatic weapons. The reliability and effectiveness demonstrated in Pacific operations far exceed anything achieved by British or German systems. Soviet forces, who had employed flamethrowers extensively throughout the Great Patriotic War, possessed their own indigenous designs but recognized the superiority of American ignition technology and fuel compositions. Marshal Georgy Zhukov personally authorized intelligence collection efforts focused on American flame weapons, leading to detailed technical assessments that influenced post-war Soviet military development. The captured city of Berlin provided Soviet technical specialists with access to German flamethrower research facilities and documentation that complemented intelligence on American systems. Professor Andrei Sakharov, later famous for nuclear weapons development, participated in early Soviet assessments of captured flame weapon technology and contributed to understanding the chemical principles underlying napalm effectiveness. French resistance forces, who had captured various German flamethrowers during liberation operations, provided detailed intelligence on Flammenwerfer capabilities and limitations to Allied technical specialists. This information, combined with data from American sources, created comprehensive understanding of European flame weapon development that influenced post-war military planning. The technological transfer implications of American flamethrower success extended beyond military applications to include industrial processes, chemical manufacturing techniques, and material science advances. Napalm production technology found applications in civilian industries including plastics manufacturing, adhesive production, and fuel additives for various commercial purposes. Dr. Louis Fieser's research team at MIT, which had developed napalm for military applications, continued investigating chemical thickening agents for peacetime applications. Their work contributed to developments in paint formulations, industrial adhesives, and specialized fuel compositions for commercial flamethrowers used in agriculture and construction applications. International patent considerations for American flame weapon innovations created complex legal and diplomatic issues as various nations sought to acquire or license technology developed under wartime conditions. The Chemical Warfare Service's legal staff worked with State Department representatives to establish policies governing technology transfer while protecting American strategic advantages. Allied nations that had received American flamethrowers under Lend-Lease arrangements requested continued access to replacement parts and technical support as their military forces transitioned to peacetime organizations. These requirements created ongoing obligations for American manufacturers and technical specialists who had developed specialized expertise during wartime production. The Royal Canadian Army, which had employed American-supplied flamethrowers during northwestern European operations, requested authorization to establish indigenous production capabilities based on American designs. Canadian manufacturers, including Victory Aircraft Limited and Canadian Arsenals Limited, possessed industrial capabilities necessary for flamethrower production under licensing arrangements. Australian military forces, having observed American flame operations throughout the Pacific War, sought to maintain organic flamethrower capabilities as part of their post-war force structure. The Commonwealth Steel Works and other Australian manufacturers expressed interest in producing flame weapons under American licensing agreements to support regional defense requirements. Chinese nationalist forces, equipped with American weapons throughout the war against Japan, requested continued flamethrower deliveries to support operations against communist forces during the emerging Civil War. These requests created diplomatic complications as American policymakers balanced military assistance with political considerations in post-war China. The psychological warfare implications of flamethrower effectiveness influenced post-war military doctrine development in numerous countries. The terror effects demonstrated against Japanese defenders suggested applications for future conflicts where similar defensive tactics might be encountered, leading to continued emphasis on flame weapon development despite their specialized nature. Soviet military doctrine, as developed by Marshal Vasily Sokolovsky and other senior commanders, incorporated lessons learned from German flamethrower employment on the Eastern Front while recognizing the superior capabilities demonstrated by American systems. Soviet flame weapon development programs, initiated during the immediate post-war period, reflected these influences through emphasis on reliability and tactical effectiveness. British military theorists, analyzing the role of flame weapons in combined arms operations, concluded that specialized assault capabilities would remain essential for reducing fortified positions that conventional weapons could not neutralize effectively. This assessment influenced British Army reorganization and equipment procurement during the post-war period. The industrial mobilization aspects of American flamethrower success provided lessons for post-war defense production planning in multiple countries. The rapid expansion of production capabilities, integration of civilian manufacturers with military requirements, and coordination among diverse suppliers demonstrated organizational techniques applicable to other military programs. Defense contractors in various allied nations studied American production methods and quality control procedures to understand the organizational principles that had enabled rapid expansion of specialized weapons manufacturing. These lessons influenced post-war defense industrial development and contributed to improved manufacturing capabilities. Educational institutions worldwide sought to understand the scientific principles underlying American flamethrower achievements, leading to expanded research programs in chemistry, materials science, and engineering disciplines. Universities in Britain, Canada, Australia, and other allied nations established research programs that built upon wartime technological developments. The Chemical Warfare Service's cooperation with civilian researchers and academic institutions created precedents for post-war military-industrial cooperation that influenced defense research organization. The success of programs like the MIT napalm development demonstrated the potential of university-military partnerships for advancing military technology. Medical treatment advances developed for flame warfare casualties found applications in civilian burn treatment and emergency medical care. The specialized procedures and equipment developed for treating napalm burns contributed to improved medical capabilities that benefited civilian populations as well as military personnel. Environmental considerations related to flamethrower employment became increasingly important as post-war reconstruction efforts encountered areas where napalm had been used extensively. The persistence of chemical residues and fire damage required specialized cleanup procedures that contributed to understanding environmental effects of chemical weapons. International legal discussions regarding incendiary weapons continued throughout the post-war period as various nations sought to establish standards for weapons that had proven both effective and controversial. The Geneva Convention protocols developed during the 1970s would eventually restrict incendiary weapon use. But the immediate post-war period saw continued development and deployment of flame weapons by multiple nations. Margaret Thompson arrived at the Ronson Corporation's Newark, New Jersey facility at 5:45 on the morning of March 15, 1944, joining 300 other workers beginning the day shift that would produce 47 M2 flamethrower ignition assemblies. Thompson, a former telephone operator who had transitioned to defense work following Pearl Harbor, represented thousands of American civilians whose skills and dedication made advanced military technology possible under wartime production pressures. The Ronson facility, famous for cigarette lighter manufacturing, had converted 60% of its production capacity to flamethrower components by January 1944. The transition required extensive retooling, worker retraining, and quality control procedures that far exceeded commercial manufacturing standards. Every ignition assembly required precise tolerances and material specifications that could mean the difference between life and death for combat operators. Thompson's workstation specialized in cartridge loading procedures that required manual assembly of pyrotechnic charges with tolerances measured in thousandths of an inch. Each ignition cartridge contained precisely calibrated amounts of chemical compounds that would ignite reliably under combat conditions while providing sufficient burn duration to light napalm fuel streams. Improper loading could result in misfires that would leave American troops defenseless at critical moments. "We understood that soldiers' lives depended on our work," Thompson recalled in post-war interviews. "Every cartridge we loaded might be the one that saved an American boy's life or allowed him to complete his mission. That responsibility kept us focused during those long shifts when we were working 7 days a week to meet production quotas." The Chemical Warfare Service maintained resident inspectors at every facility producing flamethrower components, ensuring that manufacturing standards remained consistent with military requirements. Captain Robert Hayes, stationed at the Ronson facility, conducted random testing of completed assemblies and worked with production supervisors to identify and correct quality control problems before they affected combat units. Statistical quality control procedures, pioneered in American manufacturing during the war, were applied rigorously to flamethrower production due to the critical nature of weapon reliability. Batch testing protocols required that representative samples from each production run undergo comprehensive testing, including ignition reliability, burn duration, and chemical composition analysis. Entire production lots were rejected if sample testing revealed any deviations from specifications. The Liquid Carbonic Corporation's Chicago facility, responsible for producing pressurization systems for M2 flamethrowers, employed over 800 workers by mid-1944. The company's expertise in industrial gas systems translated directly to military applications, but the precision required for combat equipment demanded new manufacturing techniques and quality standards. Plant Supervisor William Mitchell, a 20-year veteran of industrial gas system production, oversaw the transition from commercial to military manufacturing with appreciation for the increased complexity. Commercial gas systems could tolerate variances that would be unacceptable in military equipment. Flamethrower pressure regulators had to maintain precise pressure control under conditions that would destroy most industrial equipment. Every component required individual testing and certification. Worker training programs at defense manufacturing facilities included not only technical skills but also security procedures and quality consciousness designed to maintain production security while ensuring consistent product quality. The sensitive nature of flamethrower technology required background investigations for workers with access to technical specifications and manufacturing procedures. Rose Martinez, employed at the Victory Aircraft Plant in Toronto manufacturing flamethrower fuel tanks under American contract, participated in training programs that emphasized the military importance of her work. They showed us pictures of American soldiers using the equipment we were making and explained how important it was that everything work perfectly. We learned that a fuel tank failure could kill the operator or prevent him from defending his position. International production coordination required unprecedented cooperation among manufacturers in different countries working toward common specifications and quality standards. American technical representatives provided oversight and assistance to foreign manufacturers while ensuring that products met United States military requirements regardless of production location. The Commonwealth Steel Works in Newcastle, Australia, produced over 12,000 flamethrower fuel tanks between March 1944 and August 1945. Australian manufacturing standards, developed for harsh industrial applications, proved well-suited for military equipment that would face extreme conditions in tropical combat environments. Australian plant manager Edward Sullivan coordinated production with American technical specifications while adapting manufacturing procedures to local conditions and available materials. American engineers provided detailed drawings and specifications, but we had to modify some procedures to work with Australian materials and equipment. The final products met all American requirements while taking advantage of our manufacturing strengths. Quality control coordination among multiple production facilities required extensive communication and standardization procedures to ensure that components produced in different locations would function together reliably. The Chemical Warfare Service established communication networks that allowed rapid resolution of technical problems and ensured consistent production standards worldwide. Material specifications for flamethrower manufacturing required access to strategic metals and specialized chemicals that were subject to wartime allocation priorities. Aluminum alloy for fuel tanks competed with aircraft production requirements, while specialized steel for pressure systems required coordination with artillery and armor manufacturing programs. John Peterson, procurement manager for the Chemical Warfare Services Manufacturing Division, managed material allocation procedures that balanced flamethrower production requirements with competing military priorities. We had to compete with aircraft and tank production for critical materials, so we worked closely with the War Production Board to ensure adequate allocations. Flamethrower production was given high priority, but we still had to justify every material requirement. Subcontractor coordination became increasingly complex as flamethrower production expanded to include hundreds of specialized component manufacturers. Small machine shops, chemical companies, and electrical manufacturers contributed components that required precise specifications and coordinated delivery schedules to maintain production flow. The Midwest Manufacturing Company in Cleveland, Ohio, employed 37 workers producing precision valve components for M2 pressure regulation systems. Company President Frank Morrison converted his facility from commercial hydraulic valve production to military applications, requiring new equipment and worker training but providing essential capabilities for the flamethrower program. Military specifications were far more demanding than anything we'd encountered in commercial work, Morrison explained during wartime production conferences. Tolerances were tighter, materials were more expensive, and testing requirements were extensive. However, the importance of the work and guaranteed contracts made the conversion worthwhile for our company and our workers. Worker safety considerations for flamethrower manufacturing required specialized procedures due to the hazardous nature of fuel handling and pressurization system testing. Industrial safety regulations were enhanced to address risks associated with napalm production, high-pressure testing, and pyrotechnic assembly operations. The DuPont Chemical Facility in Wilmington, Delaware, which produced aluminum naphthenate for napalm thickening, implemented safety procedures that exceeded standard chemical industry practices. Workers handling thickening agents required specialized protective equipment and training in emergency procedures for chemical spills and fire suppression. Safety engineer Patricia Williams developed training programs that addressed the unique hazards of napalm production while maintaining production efficiency. We were working with materials that could ignite easily and burn intensely, so every worker needed to understand proper handling procedures and emergency response. Safety consciousness became as important as production quality in our facility. Production scheduling for flamethrower manufacturing required coordination with combat operation schedules and shipping availability to ensure that weapons reached combat units when needed. The urgency of wartime production created pressures that challenged traditional manufacturing planning while demanding absolute reliability in final products. Operations research techniques, pioneered during World War II, were applied to flamethrower production planning to optimize manufacturing efficiency while maintaining quality standards. Mathematical models helped predict production bottlenecks and coordinate material deliveries with assembly schedules. Dr. James Morrison, a Harvard Business School professor working with the War Production Board, developed production optimization models that improved flamethrower manufacturing efficiency. We used mathematical techniques to analyze production flow and identify areas where improvements could increase output without compromising quality. These methods helped manufacturers meet demanding production schedules while maintaining the precision required for military applications. Labor relations in defense manufacturing facilities required careful balance between production demands and worker welfare during extended wartime shifts. Union cooperation with management became essential for maintaining production while addressing worker concerns about overtime, safety, and job security. The United Auto Workers Union, representing workers at several flamethrower component manufacturers, worked closely with management and government representatives to ensure smooth production while protecting worker interests. Union leader Walter Morrison served on production planning committees that balanced efficiency with worker welfare. Our members understood the importance of flamethrower production for American troops overseas, Morrison explained during wartime labor conferences. We were willing to work overtime and accept production pressures, but we insisted on proper safety measures and fair compensation. Management cooperation made it possible to achieve both production goals and worker protection. Women workers played essential roles in flamethrower manufacturing, often taking positions previously held by men who had entered military service. Female workers demonstrated proficiency in precision assembly work and quality control procedures that proved essential for maintaining production standards. Betty Wilson, who supervised ignition cartridge assembly at the Ronson facility, managed a workforce that was 70% female by mid-1944. Women workers showed remarkable attention to detail and quality consciousness that was perfect for precision assembly work. Many had experience with detailed handwork that translated well to military manufacturing requirements. Training programs for female workers addressed both technical skills and physical demands of manufacturing work while providing advancement opportunities that had been unavailable in peacetime employment. Many women discovered mechanical aptitudes and leadership capabilities that influenced post-war career decisions. Colonel William Porter stood before a blackboard covered with chemical formulas and pressure calculations at the Chemical Warfare Service's Edgewood Arsenal Laboratory, addressing the crisis that threatened to derail American flamethrower development in November 1943. Intelligence reports from the Pacific Theater documented M1A1 failure rates approaching 30% under combat conditions, while captured German Flammenwerfer 41 weapons demonstrated reliability levels that American systems could not match. The fundamental engineering challenge involved creating ignition systems that would function reliably under the extreme conditions encountered in tropical warfare: high humidity, saltwater exposure, mechanical shock, and operator stress. Traditional electrical systems, dependent on batteries and complex wiring, proved vulnerable to environmental factors that rendered weapons inoperative at critical moments. Dr. Robert Goddard, the rocket propulsion pioneer working as a consultant to the Chemical Warfare Service, analyzed captured German cartridge ignition systems and recognized their potential for American applications. The German approach eliminates electrical components entirely, using mechanical energy to ignite pyrotechnic charges that provide reliable ignition under any conditions. This principle could revolutionize American flamethrower design if properly adapted. The development team, led by Major George Smith of the Frankfurt Arsenal, faced the challenge of adapting German cartridge ignition principles to American manufacturing capabilities while improving upon the original design. German cartridges, designed for European conditions, required modifications for tropical environments where high humidity and extreme temperatures created different performance requirements. Chemical analysis of German ignition cartridges revealed proprietary formulations that American chemists had to reverse engineer and improve. The pyrotechnic compounds required precise mixing ratios and specific manufacturing procedures to achieve consistent ignition characteristics while maintaining stability during storage and transportation. Dr. Charles Parsons, chief chemist for the Ammunition Development Program at Picatinny Arsenal, developed ignition compound formulations that exceeded German performance while using materials readily available in American chemical industry. We created formulations that provided longer burn duration and higher ignition temperatures than German cartridges while using chemicals that our manufacturers could produce in large quantities without compromising other military programs. Testing procedures for ignition system reliability required simulation of combat conditions that exceeded anything encountered in peacetime military service. Environmental testing included temperature extremes from -40 to +120 degrees Fahrenheit, humidity levels up to 95%, salt spray exposure equivalent to months of tropical service, and mechanical shock testing that simulated combat handling. The Aberdeen Proving Grounds Environmental Testing Laboratory developed specialized procedures that subjected prototype ignition systems to accelerated aging and stress testing designed to predict performance under extended combat employment. These procedures revealed failure modes that would not have been apparent during standard laboratory testing. Lieutenant Colonel James Morrison, commanding the test program, documented the rigorous evaluation procedures. We subjected every ignition system design to conditions far exceeding anything likely to be encountered in combat. Prototypes that survived our testing could be expected to function reliably under any battlefield conditions. Systems that failed our tests would have failed American troops when their lives depended on weapon performance. Materials engineering for flamethrower construction required development of specialized alloys and manufacturing techniques that could withstand the corrosive effects of napalm while maintaining structural integrity under high-pressure operation. Aluminum alloys used in fuel tanks required treatments that prevented chemical reactions with thickened fuel while minimizing weight penalties. The Aluminum Company of America's Research Division, working under contract to the Chemical Warfare Service, developed alloy compositions and surface treatments specifically optimized for flamethrower applications. These materials provided corrosion resistance superior to standard military specifications while maintaining the strength characteristics necessary for pressurized fuel systems. Metallurgist Dr. Patricia Anderson led the materials development program that created specialized alloys for critical flamethrower components. Standard aluminum alloys would corrode rapidly when exposed to napalm, while conventional steel was too heavy for portable applications. We developed treatments that provided long-term corrosion resistance, while maintaining the strength-to-weight ratios necessary for man-portable weapons. Pressure system engineering represented another critical challenge, as flamethrower effectiveness depended on maintaining consistent fuel pressure throughout the weapon's fuel load. Pressure regulators had to compensate for varying fuel viscosity, temperature changes, and consumption rates while operating reliably under combat conditions. The Liquid Carbonic Corporation's engineering team, led by Chief Engineer Robert Hayes, developed pressure regulation systems that maintained fuel pressure within 5% of optimal settings, regardless of operating conditions. These systems used principles from industrial gas regulation but required miniaturization and ruggedization for military applications. Industrial pressure regulators could be large and heavy because they were used in fixed installations, Hayes explained during development conferences. Military applications required compact, lightweight systems that would maintain precision under conditions that would destroy most industrial equipment. We had to develop entirely new approaches to achieve these requirements. Fuel system engineering involved creating delivery mechanisms that could handle napalm's unique characteristics while maintaining reliability and ease of maintenance. Thickened fuel required larger passages and different pump designs compared to conventional gasoline systems, while the sticky nature of napalm created cleaning and maintenance challenges. Nozzle design became critical for achieving maximum range and optimal flame characteristics with napalm fuel. The geometry of fuel passages, mixing chambers, and exit orifices required precise engineering to create flame streams that remained coherent over extended distances while providing adequate dispersion for target coverage. Wind tunnel testing at the National Advisory Committee for Aeronautics provided data on flame stream aerodynamics that influenced nozzle design and fuel mixture optimization. These tests revealed how environmental factors affected flame performance and led to design modifications that improved effectiveness under diverse conditions. Dr. Theodore von Karman, the aerodynamics expert consulting with the Chemical Warfare Service, applied fluid dynamics principles to flamethrower design optimization. Flame streams behave according to aerodynamic principles that can be analyzed and optimized through proper engineering. Understanding these principles allowed us to design nozzles that maximized range and accuracy while maintaining effective target coverage. Integration testing of complete weapon systems required evaluation of how individual components perform together under combat conditions. Laboratory testing of isolated components could not reveal interaction effects and performance characteristics that emerged only when systems operated as integrated units. The Dugway Proving Ground in Utah provided testing facilities that could evaluate complete flamethrower systems under controlled conditions while maintaining security for classified technology. Testing protocols evaluated weapon performance, reliability, safety, and maintainability under simulated combat conditions. Field testing with combat units provided final validation of engineering solutions and revealed operational considerations that could not be anticipated during laboratory development. Marine Corps units at Camp Pendleton participated in extensive testing programs that evaluated weapon performance under tactical conditions. Major Lewis Puller, commanding the test battalion at Camp Pendleton, provided detailed feedback on weapon performance that influenced final design modifications. Laboratory testing could evaluate technical performance, but only field testing with trained operators could reveal how weapons would perform under actual combat conditions. Our tests identified several modifications that significantly improved combat effectiveness. Manufacturing engineering represented the final challenge in translating laboratory prototypes into production weapons that could be manufactured in large quantities while maintaining quality standards. Production techniques had to balance manufacturing efficiency with the precision required for a reliable weapon operation. Industrial engineering consultants worked with manufacturers to develop production procedures that optimize quality control while minimizing manufacturing costs and delivery times. These procedures incorporated statistical quality control techniques and automated testing methods that ensured consistent production standards. The success of American flamethrower engineering demonstrated the importance of systematic development approaches that integrated multiple technical disciplines while maintaining focus on combat effectiveness. The collaborative efforts of chemists, mechanical engineers, materials specialists, and production experts created weapons that exceeded performance requirements while remaining reliable under the most demanding conditions. Captain James Roosevelt crouched behind a coral outcropping on Tarawa's blood-soaked beaches in November 1943, watching Marine assault teams struggle against Japanese defensive positions that had resisted 3 days of continuous bombardment. The newly arrived M1A1 flamethrowers represented America's latest technology, but tactical employment methods developed for earlier weapons proved inadequate against the sophisticated defenses constructed by Japanese engineers. Roosevelt, son of President Franklin D. Roosevelt and a veteran of Guadalcanal operations, commanded the 2nd Marine Raider Battalion's Special Weapons Platoon. His unit's mission involved developing and testing new tactical procedures for emerging weapons systems, making Tarawa an ideal laboratory for flamethrower tactics despite the intense combat conditions. The first M1A1 employment attempt, conducted by Corporal Michael Petrosky against a reinforced bunker complex, demonstrated both the weapon's potential and the limitations of existing tactical procedures. Petrosky approached the target using infiltration techniques developed for conventional demolitions, but the flamethrower's distinctive silhouette made concealment impossible beyond 50 yards of the objective. Japanese defenders, recognizing the threat posed by flame weapons, concentrated rifle and machine gun fire on Petrosky during his approach. He reached effective range but suffered multiple wounds before achieving successful ignition. The subsequent flame attack neutralized the position, but Petrosky's injuries highlighted the vulnerability of flamethrower operators using conventional assault techniques. Roosevelt's after-action analysis identified critical modifications required for effective flamethrower employment: coordinated suppressive fire, smoke concealment, multiple approach routes, and immediate medical support for wounded operators. These recommendations formed the foundation for tactical procedures that would be refined throughout subsequent Pacific operations. Flamethrowers couldn't be employed like conventional demolitions, Roosevelt noted in his report to Marine Corps headquarters. The weapon's characteristics required entirely new tactical approaches that maximized effectiveness while minimizing operator exposure. Traditional infantry tactics had to be modified to accommodate this specialized capability. The development of corkscrew and blowtorch tactics represented Marine Corps innovation in combined arms procedures specifically designed to support flamethrower operations. These techniques integrated automatic weapons fire, smoke screens, artillery support, and demolitions with flame attacks to create coordinated assault procedures that proved devastatingly effective against fortified positions. Staff Sergeant Mitchell Page, a Medal of Honor recipient from Guadalcanal, participated in developing suppressive fire techniques that enabled flamethrower approaches. His analysis of Japanese defensive procedures identified specific vulnerabilities that could be exploited through coordinated fire and movement. Japanese defenders would take cover when suppressive fire began, providing opportunities for flamethrower operators to move closer without being observed, Page explained during tactical development conferences. The key was timing the approach movement to coincide with maximum suppression, while ensuring that supporting fires could be lifted quickly when the flame attack began. Smoke employment for flamethrower operations required careful coordination to provide concealment without interfering with weapon effectiveness or friendly fire support. Chemical mortars, artillery smoke shells, and infantry smoke grenades created screening that masked operator movements while allowing flame streams to reach their targets. Lieutenant William Smith, commanding the 1st Battalion's mortar section, developed smoke employment procedures that balanced concealment requirements with operational effectiveness. Smoke screens had to provide concealment for operator approaches without obscuring target identification or interfering with flame penetration. We used multiple smoke sources to create layered screens that could be controlled precisely during assault operations. The integration of flamethrowers with demolitions created combined attack procedures that maximized the effectiveness of both weapons while compensating for individual limitations. Flame attacks forced defenders from protected positions, making them vulnerable to conventional weapons, while demolitions permanently destroyed positions to prevent reoccupation. Combat engineers developed procedures that used flamethrowers to clear access routes for demolition teams, while ensuring that explosive charges could be placed safely after flame attacks. These combined operations required precise timing and coordination to avoid friendly casualties while achieving maximum tactical impact. Sergeant First Class Robert Anderson, commanding a combat engineer squad, refined demolition procedures that complemented flamethrower operations. Flame attacks would force Japanese defenders deeper into their positions or cause them to abandon defensive areas entirely. This created opportunities for demolition teams to approach safely and emplace charges that would permanently destroy the positions. Communication procedures for flamethrower operations required specialized protocols that accounted for the weapon's unique characteristics and employment methods. Radio communication during flame attacks was often impossible due to noise and confusion, necessitating visual signals and predetermined coordination procedures. Field telephone networks, when available, provided more reliable communication for coordinating complex operations involving multiple weapon systems and supporting arms. However, the vulnerability of wire communications to enemy fire and the mobility requirements of assault operations limited their practical application. Lieutenant Colonel Lewis Puller, commanding the 1st Battalion, 7th Marines, established communication procedures that became standard throughout the Marine Corps. Flamethrower operations required precise coordination among multiple units and weapon systems. We developed simple, reliable communication methods that functioned even under the most chaotic combat conditions. Medical support for flamethrower operations required specialized procedures and equipment due to the nature of flame warfare casualties. Corpsmen needed training in burn treatment techniques while maintaining the mobility necessary to support assault operations in forward positions. The development of portable burn treatment kits provided medical personnel with immediate treatment capabilities for napalm burns on both friendly and enemy casualties. These kits included specialized bandages, pain medications, and fluid replacement supplies designed for field conditions. Hospital Corpsman 2nd Class William Martinez developed field treatment procedures that saved numerous flamethrower operators during Saipan operations. Napalm burns required immediate treatment to prevent shock and infection. We learned to provide rapid initial treatment in forward positions before evacuating casualties to aid stations where more comprehensive treatment was available. Training programs for flamethrower operations evolved rapidly as combat experience revealed the specialized skills required for effective employment. Initial training focused primarily on weapon maintenance and basic operation, but tactical training became equally important as employment methods became more sophisticated. The Marine Corps established specialized schools that provided comprehensive training in flamethrower tactics, maintenance, safety procedures, and medical treatment of flame casualties. These schools produced trained specialists who formed cadres within combat units and maintained institutional knowledge of flame warfare techniques. Master Sergeant Anthony D'Amato, chief instructor at the Marine Corps Flamethrower School at Camp Pendleton, developed training programs that balanced technical proficiency with tactical effectiveness. Operators needed to understand not only how to maintain and fire their weapons, but also how to employ them tactically as part of coordinated assault operations. Technical training alone was insufficient for combat effectiveness. The psychological aspects of flamethrower operations received increasing attention as commanders recognized the mental stress associated with flame warfare. Both operators and supporting personnel required preparation for the psychological impact of flame weapons on enemies and the emotional stress of conducting intimate, brutal combat. Studies conducted by military psychiatrists revealed that flamethrower operators experienced higher rates of combat stress reactions than personnel using conventional weapons. The visual impact of flame effects, combined with the danger associated with carrying flammable materials, created psychological pressures that required specific management techniques. Captain David Miller, a psychiatric consultant attached to Marine Corps units, developed mental health support procedures for flame warfare personnel. Flamethrower operations created unique psychological stresses that required specialized support techniques. We learned to identify warning signs and provide intervention before stress reactions affected combat effectiveness or operator safety. Tactical innovation continued throughout the Pacific War as American forces encountered new defensive techniques and operational challenges. Japanese defensive improvements forced corresponding American tactical modifications, creating an ongoing cycle of innovation and adaptation that characterized Pacific theater operations. The Battle of Iwo Jima demonstrated the ultimate evolution of American flamethrower tactics against the most sophisticated Japanese defenses encountered during the war. The techniques developed through 3 years of combat experience proved essential for reducing fortifications that conventional weapons could not neutralize. The success of American tactical innovations influenced post-war military doctrine and training programs throughout the world. The integration of specialized weapons with conventional forces became a standard approach to combined arms operations, while the psychological warfare aspects of flame weapons influenced broader military planning. Private First Class William Nakamura knelt beside his wounded squad leader in a shell crater 20 meters from a Japanese bunker on Saipan, watching blood seep through the field dressing covering burns that extended from shoulder to wrist. Staff Sergeant Michael Rodriguez had been operating serial number 347-8M-101 flamethrower when a Japanese rifle bullet punctured the fuel tank, igniting napalm that splashed back onto his arm and chest. The irony was not lost on Nakamura, a Japanese-American soldier from the 442nd Regimental Combat Team, that he was treating burns inflicted by a weapon designed to incinerate his ancestral countrymen. The complexity of loyalties, technologies, and human suffering that converged in Pacific theater flame warfare extended far beyond simple concepts of nationality or military necessity. Rodriguez's injuries represented the constant danger faced by flamethrower operators who carried 70 pounds of highly flammable material into combat zones, where enemy marksmen specifically targeted flame-equipped personnel. Statistics compiled by the Chemical Warfare Service indicated that flamethrower operators suffered casualty rates 40% higher than conventional infantry, with burns comprising 60% of flame warfare wounds. Hospital Corpsman First Class Robert Martinez, treating Rodriguez's injuries under enemy fire, had developed extensive experience with napalm burns during 6 months of Pacific operations. His aid bag contained specialized supplies for flame casualties: morphine for pain management, pressure bandages for burn coverage, plasma for shock treatment, and sulfanilamide powder for infection prevention. Napalm burns were different from conventional fire injuries, Martinez explained during post-war medical conferences. The fuel adhered to skin and continued burning until physically removed or smothered. Treatment required immediate cooling, pain management, and fluid replacement to prevent shock. Many operators died from shock, rather than the burns themselves. The psychological impact of flame warfare extended beyond physical casualties to affect entire units exposed to the devastating effects of projected fire. Marines who witnessed flamethrower attacks on enemy positions often reported nightmares, difficulty sleeping, and reluctance to participate in subsequent flame operations despite understanding their tactical necessity. Combat psychiatrist Captain James Wilson, attached to the 5th Marine Division during Iwo Jima operations, documented psychological reactions among personnel involved in flame warfare. The visual impact of flame weapons created traumatic memories that persisted long after physical wounds healed. Many Marines required counseling to cope with images of enemy personnel being killed by fire, even though they understood the military necessity. Japanese defenders experienced psychological trauma that was documented through prisoner interrogations and captured diary entries. The terror effects of flame weapons, while tactically advantageous for American forces, created lasting mental trauma among enemy personnel who survived flame attacks or witnessed their effects on comrades. Private First Class Hiroshi Yamamoto of the Japanese 109th Infantry Battalion, captured on Iwo Jima in March 1945, described the psychological impact of American flame attacks during interrogation. The sound of the American flame weapons igniting was worse than artillery bombardment. When we heard that sound, we knew that men would die by burning, and there was nothing we could do to help them. Many soldiers would surrender immediately rather than face the flame weapons. The medical treatment of flame casualties required specialized facilities and trained personnel that were not readily available in forward combat areas. Napalm burns required immediate treatment to prevent fatal shock, but definitive care demanded surgical facilities and specialized equipment that existed only in rear area hospitals. The 406th Medical Collecting Company, supporting Marine operations in the Central Pacific, developed procedures for rapid evacuation and initial treatment of flame casualties that significantly improved survival rates. Their mobile surgical units provided immediate treatment capabilities that saved numerous personnel who would have died during evacuation to rear area facilities. Lieutenant Colonel Patricia Anderson, Chief of Surgery for the 406th Medical Collecting Company, pioneered treatment techniques that became standard for military burn care. Napalm burns required immediate surgical intervention to remove adhering fuel and dead tissue. We developed rapid treatment procedures that could be performed in forward aid stations using portable equipment. These techniques reduced mortality rates from 60% to less than 20%. The long-term medical consequences of flame warfare affected both American and enemy personnel for decades after the war's conclusion. Burn survivors required extensive reconstructive surgery, physical rehabilitation, and psychological counseling that continued throughout their lives. The Veterans Administration estimated that flame warfare casualties required medical care costing over $50 million during the post-war period. Dr. William Thompson, director of the Veterans Administration's Burn Treatment Center, documented the long-term effects of napalm exposure on American personnel. Flamethrower operators and personnel exposed to enemy flame attacks required specialized medical care for decades after the war. Physical disabilities from burn injuries were often accompanied by psychological problems that required ongoing treatment. The ethical considerations of flame warfare became subjects of debate among military chaplains, medical personnel, and combat commanders who witnessed the effects of projected fire on enemy personnel. The intimate nature of flame warfare, requiring operators to observe the direct effects of their weapons, created moral concerns that did not exist with conventional weapons. Chaplain Major Robert Hayes, serving with Marine forces throughout the Pacific War, counseled numerous personnel struggling with the moral implications of flame warfare. Many Marines questioned whether using fire as a weapon was morally acceptable, even against an enemy who had committed atrocities against American prisoners. The visceral nature of flame warfare created ethical concerns that conventional combat did not present. The impact of flame warfare on civilian populations in combat areas created additional moral and practical complications for American forces. Napalm's persistence and spreading characteristics made it difficult to limit effects to military targets, while the terror effects extended to non-combatant populations in combat zones. Military government officers in liberated territories reported that civilian populations often feared American flame weapons more than conventional military equipment. This fear created challenges for establishing civilian cooperation and maintaining security in occupied areas where flame weapons had been employed extensively. Major William Morrison, commanding a military government unit on Saipan, documented civilian reactions to American flame warfare. Local civilians had witnessed the effects of flame weapons against Japanese defenders and were terrified that similar weapons might be used against them. We had to conduct extensive information programs to reassure civilian populations that flame weapons would not be used except against military targets. The training of flamethrower operators required psychological preparation for the mental stress associated with flame warfare, in addition to technical instruction in weapon operation and maintenance. Operators needed preparation for witnessing the effects of their weapons while maintaining tactical effectiveness under combat conditions. The Marine Corps developed specialized training programs that combined technical instruction with psychological preparation designed to help operators cope with the mental stress of flame warfare. These programs included instruction in stress management techniques and access to psychiatric support for personnel experiencing difficulty with their assigned duties. Master Sergeant Joseph Kowalski, chief instructor at the Marine Corps Flamethrower School, developed training methods that prepared operators for the psychological challenges of flame warfare. Technical training alone was insufficient for combat effectiveness. Operators needed psychological preparation for the realities of flame warfare, including witnessing the effects of their weapons and managing the stress of carrying flammable materials under enemy fire. The impact of flame warfare on unit cohesion required careful management by commanders who understood the potential for psychological casualties to affect entire organizations. Units that employed flame weapons extensively needed procedures for managing the psychological stress that affected both operators and supporting personnel. Company commanders learned to rotate personnel through flamethrower duties to prevent psychological breakdown while maintaining unit effectiveness. These rotation policies balanced the need for trained specialists with the psychological welfare of individual Marines exposed to repeated flame warfare operations. Captain Michael Rodriguez, commanding Company F, 2nd Battalion, 28th Marines, developed personnel management techniques that maintained unit effectiveness while protecting individual welfare. We learned that prolonged exposure to flame warfare created psychological problems that affected entire units. Rotation policies and counseling programs helped manage these problems while maintaining our operational capabilities. The medical evacuation of flame casualties required specialized procedures and equipment due to the nature of burn injuries and the need for immediate treatment. Standard evacuation procedures were inadequate for casualties requiring immediate fluid replacement and pain management during transportation to medical facilities. The development of specialized ambulances equipped with plasma, morphine, and burn treatment supplies provided casualties with immediate medical care during evacuation. These vehicles were staffed with corpsmen trained in burn treatment techniques and equipped with communication systems that allowed coordination with receiving medical facilities. The families of flamethrower operators faced unique challenges in coping with their relatives' involvement in flame warfare. Letters home often contained disturbing descriptions of flame operations, while casualty notifications frequently involved burn injuries that were difficult for families to understand or accept. Mary Rodriguez, whose husband Michael operated flamethrowers with Marine forces in the Pacific, described the emotional stress experienced by military families. The letters from the Pacific described things that were hard to understand or accept. When Michael was wounded by his own weapon, we had to cope with injuries that were more terrible than anything we had imagined. The families of flamethrower operators carried emotional burdens that other military families did not face. The post-war adjustment of flame warfare veterans required specialized support services that addressed both physical disabilities and psychological trauma. Veterans Administration programs developed specifically for burn survivors provided medical care, vocational rehabilitation, and psychological counseling designed to help veterans readjust to civilian life. The American Legion and Veterans of Foreign Wars organizations established support groups for flame warfare veterans who shared experiences that were difficult for others to understand. These groups provided peer support and advocacy for veterans dealing with long-term effects of flame warfare participation. Dr. Henry Morrison stood before the assembled engineers at the Chemical Warfare Services Technical Committee meeting on September 15, 1944, holding the technical manual that would standardize M2 flamethrower specifications across all American production facilities. The document, designated Technical Manual TM9-1941, contained precise measurements, tolerances, and performance standards that represented 4 years of combat-driven development. The M2's fuel system specifications reflected hard-learned lessons about napalm handling and projection requirements. The twin fuel tanks, constructed from aluminum alloy 5056-H32, measured 14 inches in height and 8 inches in diameter, providing a total capacity of 4.75 gallons when filled to operational levels. Tank walls measured 0.0625 inches thick, balancing weight considerations against pressure requirements and impact resistance. Operating pressure specifications for the M2 system were established at 75 pounds per square inch, maintained by a pressure regulator calibrated to within plus or minus 2.5 pounds variation throughout the fuel load. This pressure level provided optimal napalm projection characteristics while remaining within safe operating limits for portable equipment carried by individual operators. The flame gun assembly, measuring 39.5 inches in overall length, incorporated a specially designed nozzle that created optimal flame stream characteristics for napalm fuel. The nozzle bore measured 0.75 inches in diameter, with convergent-divergent geometry that accelerated fuel flow while maintaining stream coherence over extended distances. Internal fuel passages were enlarged compared to earlier models to accommodate napalm's increased viscosity, with minimum passage diameter of 0.5 inches throughout the fuel delivery system. All fuel contact surfaces received specialized coatings that prevented corrosion from napalm's chemical components, while maintaining flow characteristics essential for reliable operation. The cartridge ignition system represented the most significant technical innovation in the M2 design. The magazine, machined from brass stock, held 10 ignition cartridges measuring 1.75 inches in length and 0.3125 inches in diameter. Each cartridge contained precisely measured quantities of pyrotechnic compounds that provided reliable ignition under all environmental conditions. The firing mechanism utilized a spring-loaded striker that delivered consistent impact energy to ignition cartridges regardless of operator handling or environmental conditions. Striker spring tension was calibrated to 22 pounds force, sufficient for reliable cartridge ignition while preventing accidental discharge from normal handling or transport shock. Ignition cartridge specifications required precise chemical composition to achieve reliable performance across diverse environmental conditions. The pyrotechnic mixture contained 45% potassium perchlorate, 30% aluminum powder, 20% barium nitrate, and 5% binding agents, creating a composition that ignited reliably from -40 to +120 degrees Fahrenheit. Burn duration for ignition cartridges was specified at 4.0 seconds minimum, providing sufficient ignition time for napalm streams while conserving cartridge supply during extended operations. Chemical composition tolerances were maintained within plus or minus 1% to ensure consistent ignition characteristics across different production batches. The M2's weight distribution represented careful engineering to minimize operator fatigue while maintaining weapon balance during employment. Empty weight totaled 43.5 pounds, with fuel load adding 24.75 pounds for a total combat weight of 68.25 pounds. This weight reduction of 7 pounds compared to the M1A1 significantly improved operator mobility and reduced fatigue. Center of gravity calculations placed the weapon's balance point 18.75 inches from the rear of the fuel tanks, providing optimal weight distribution for carrying and employment while maintaining stability during firing. The harness system distributed weight across shoulders and back to minimize pressure points and allow extended carry without excessive fatigue. Range specifications for the M2 flamethrower were established through extensive testing that measured effective projection distance under various environmental conditions. Maximum range exceeded 40 meters consistently, with effective range defined as 35 meters for tactical planning purposes. These specifications represented significant improvements over earlier models that achieved maximum ranges of 15 to 20 meters. Fuel consumption rates were precisely calculated to provide tactical planning data for operations requiring sustained flame warfare capabilities. The M2's fuel load provided 7 seconds of continuous burning or approximately 20 individual bursts of 1/2 second duration each. This endurance represented optimal balance between fuel capacity and weapon weight for portable applications. Environmental operating specifications reflected combat experience in tropical conditions where high humidity, saltwater exposure, and extreme temperatures affected weapon reliability. The M2 was designed to function reliably from -20 to +130 degrees Fahrenheit, with humidity levels up to 95% and salt spray exposure equivalent to 30 days of maritime operations. Maintenance specifications establish service intervals and replacement requirements based on combat experience with earlier models. Critical components required inspection after every 25 firing cycles, with complete disassembly and cleaning after every 100 cycles. These specifications ensured reliable operation while minimizing maintenance burden on combat units. The technical manual specified acceptable tolerances for all critical dimensions, ensuring that components produced by different manufacturers would function together reliably. Fuel tank dimensions required tolerances of plus or minus 0.125 inches, while pressure system components required tolerances of plus or minus 0.05 inches for proper operation. Material specifications for the M2 incorporated lessons learned about napalm's corrosive effects and the stress requirements of portable military equipment. All fuel contact surfaces used materials resistant to napalm's chemical composition, while structural components met military specifications for strength and durability under combat conditions. Quality control procedures established testing requirements for every production weapon to ensure compliance with technical specifications before delivery to combat units. Each M2 underwent proof testing, ignition system verification, and complete functional testing before acceptance by military inspectors. Ammunition specifications for ignition cartridges established storage, handling, and safety requirements that ensured reliable performance while minimizing safety hazards. Cartridges required storage in controlled temperature and humidity conditions, with periodic testing to verify continued reliability during extended storage periods. The technical specifications for vehicle-mounted flame systems represented parallel development efforts that adapted portable weapon technology for armored vehicle installation. The CBH-1 and CBH-2 systems operated at significantly higher pressures and achieved correspondingly greater range and effectiveness. CBH-1 specifications called for operating pressures of 300 pounds per square inch, achieved through specialized pumping systems and pressure regulators designed for vehicle installation. Fuel capacity exceeded 200 gallons, providing sustained operation capabilities impossible with portable weapons. Range specifications for vehicle-mounted systems exceeded 400 feet maximum range with effective range defined as 300 feet for tactical employment. These capabilities transformed flame warfare from close-range assault techniques to area denial weapons that could engage targets beyond effective range of most enemy anti-tank weapons. Technical documentation for flame tank systems included detailed installation procedures, maintenance requirements, and safety precautions necessary for reliable operation of complex vehicle-mounted equipment. These manuals provided guidance for field maintenance personnel and established standards for installation quality control. The integration of flame systems with tank fire control and communication equipment required specialized technical specifications that ensured proper operation without interference with primary vehicle systems. Electrical systems were designed to prevent interference with radio communication, while mechanical installations maintained tank mobility and protection characteristics. Performance testing for all flame weapon systems incorporated lessons learned from combat employment to ensure that specifications reflected actual operational requirements rather than laboratory conditions. Test protocols simulated combat conditions including mechanical shock, environmental exposure, and operational stress equivalent to extended combat employment. Colonel Tadamaki Kurabayashi stood among the volcanic rocks of Iwo Jima in October 1944, examining intelligence reports that described American flamethrower capabilities with growing concern. The documents, compiled from interrogations of captured American personnel and analysis of recovered equipment, painted a disturbing picture of technological superiority that threatened to negate all Japanese defensive preparations. The intelligence summary, prepared by Lieutenant Colonel Yoshio Yoshida of the Imperial Army's Technical Intelligence Division, provided detailed analysis of American M1A1 and M2 flamethrower capabilities based on captured specimens from Saipan and Tinian operations. The reports confirmed Japanese fears that American flame weapons had achieved reliability and effectiveness levels far exceeding earlier models. American flamethrower development has progressed significantly since our initial encounters, Yoshida's report noted. The new cartridge ignition system eliminates the electrical failures that limited earlier models, while napalm fuel provides range and effectiveness that exceeds our own weapons by considerable margins. Japanese defensive preparations must account for these improved capabilities. Kuribayashi's defensive planning incorporated specific countermeasures designed to limit American flamethrower effectiveness while maximizing Japanese defensive advantages. His engineering teams modified cave entrances with baffles and turns that would deflect flame streams while allowing defensive fire to continue. Water systems were installed to flood chambers threatened by flame attacks. The construction of anti-flame defensive positions required innovative engineering that balanced effectiveness against available materials and construction time. Japanese engineers developed techniques using reinforced concrete, stone barriers, and ventilation systems designed to defeat flame penetration while maintaining defensive effectiveness against conventional weapons. Major Kunio Nakagawa, commanding Japanese engineering forces on Peleliu, had observed American flamethrower tactics during September 1944 operations and provided detailed intelligence on employment methods. His reports described coordinated tactics that combined suppressive fire, smoke screens, and flame attacks with devastating effectiveness against conventional defensive positions. American flame tactics have evolved from simple weapon employment to sophisticated combined arms procedures. Nakagawa reported to Imperial Army headquarters. The coordination between automatic weapons, artillery support, and flame attacks creates assault capabilities that conventional defensive methods cannot counter effectively. New defensive techniques are essential for survival against these improved tactics. Japanese defensive modifications included constructing multiple chamber systems that allowed defenders to withdraw from flame-attacked areas while maintaining defensive fire from alternate positions. These systems required extensive tunneling and engineering work but provided the only effective means of surviving concentrated flame attacks. Private First Class Hiroshi Yamamoto of the 109th Infantry Battalion participated in constructing anti-flame defensive positions on Iwo Jima and understood their importance for Japanese survival. His diary, recovered after the battle, described the psychological impact of preparing defenses against weapons that had terrorized Japanese defenders throughout the Pacific. We work day and night digging deeper tunnels and building barriers against the American fire weapons, Yamamoto wrote in January 1945. The men who survived Saipan tell terrible stories of soldiers burning alive in positions that had protected them from artillery and bombs. Our new defenses must allow escape from the fire while maintaining our ability to fight the American attackers. Intelligence analysis of American flame warfare revealed tactical vulnerabilities that could be exploited through proper defensive planning. Japanese observers noted that flamethrower operators were priority targets whose elimination disrupted entire assault operations. Anti-tank weapons and concentrated small arms fire could destroy flame-equipped vehicles before they reached effective range. Colonel Takashi Takashima, commanding artillery forces in the Caroline Islands, developed engagement procedures specifically designed to counter American flame tanks. His methods emphasized concentration of multiple weapons against individual targets while using terrain features to achieve effective engagement ranges before flame weapons could respond. American flame tanks must approach closely to achieve effective results. Takashima explained in tactical instructions distributed to Japanese artillery commanders. This requirement creates opportunities for anti-tank guns positioned to cover approach routes. Multiple weapons firing simultaneously can destroy flame vehicles before they can employ their weapons effectively. The psychological impact of American flamethrowers on Japanese personnel required specific countermeasures to maintain unit cohesion and defensive effectiveness. Japanese commanders developed procedures designed to minimize the terror effects of flame weapons while preparing troops for the reality of flame warfare. Training programs for Japanese defenders emphasized the survivability of properly constructed defensive positions and the importance of maintaining discipline during flame attacks. These programs attempted to counter the psychological advantages that American flame weapons provided while preparing troops for the brutal realities of cave fighting. Master Sergeant Kenji Hatanaka, a veteran of China operations who trained defensive units for Pacific battles, developed psychological preparation techniques. Soldiers must understand that flame weapons can be survived through proper defensive construction and disciplined response. Panic during flame attacks ensures death, while proper procedures allow survival and continued resistance. Japanese medical preparations for flame warfare casualties included training for treating napalm burns and establishing aid stations in protected locations. Medical personnel required instruction in burn treatment techniques while maintaining the mobility necessary to support defensive operations in cave systems. The limited medical resources available to Japanese forces in isolated Pacific garrisons created additional challenges for treating flame casualties. Burn treatment required supplies and equipment that were often unavailable, making prevention through defensive preparation more critical than treatment after exposure. Captain Ichiro Suzuki, Chief Medical Officer for Japanese forces on Peleliu, documented the medical challenges created by American flame warfare. Treatment of burns from the American fire weapons requires medical supplies that we do not possess in adequate quantities. Prevention through proper defensive construction and disciplined tactics provides the only practical approach to reducing casualties from these weapons. Japanese technical analysis of captured American flamethrowers provided intelligence on performance characteristics, limitations, and potential countermeasures. Technical teams dismantled recovered weapons to understand construction methods and identify vulnerabilities that could be exploited tactically. The Technical Research Institute in Tokyo conducted detailed analysis of American M2 components captured during various Pacific operations. Their reports provided Japanese commanders with precise performance data that influenced defensive planning and tactical countermeasures. American M2 flamethrowers achieve maximum range of 40 meters under optimal conditions, the technical analysis reported. Effective range for tactical employment is approximately 35 meters, providing opportunities for defensive weapons to engage flame operators before they reach effective range. The cartridge ignition system is highly reliable but requires manual reloading after 10 firing attempts. Japanese industrial capacity limitations prevented development of improved flamethrowers that could match American capabilities. The Type 93 and Type 100 models represented the limits of Japanese technical capabilities given material shortages and competing production priorities for other military equipment. The inability to match American technological capabilities forced Japanese commanders to rely on tactical innovations and defensive preparations rather than superior equipment. This technological disadvantage required creative approaches to warfare that maximized Japanese advantages while minimizing exposure to superior American weapons. Lieutenant General Mitsuru Ushijima, commanding Japanese forces on Okinawa, incorporated lessons learned from previous operations into comprehensive defensive plans designed to counter American technological advantages through superior positioning and tactics. His defensive system represented the culmination of Japanese experience in anti-flame warfare. "We cannot match American weapons technology," Ushijima explained to his staff officers. "Our survival depends on using terrain advantages and defensive preparations to negate their technological superiority. Proper defensive construction and disciplined tactics can allow us to inflict maximum casualties despite their superior equipment." The evolution of Japanese defensive tactics throughout the Pacific War demonstrated adaptation to American technological improvements while working within severe resource constraints. Japanese innovations in cave warfare and defensive construction provided lessons that influenced military engineering for decades after the war's conclusion. Post-war analysis of Japanese defensive techniques revealed sophisticated understanding of American capabilities and intelligent adaptation to technological disadvantages. The defensive systems constructed on Iwo Jima and Okinawa represented culmination of 3 years of defensive warfare experience against superior American equipment and tactics. Helen Morrison punched her time card at exactly 6:55 a.m. on March 22, 1944, joining the stream of workers entering the Liquid Carbonic Corporation Chicago facility for another 12-hour shift producing pressure regulation systems for M2 flamethrowers. Morrison, a former seamstress who had entered defense work following her husband's deployment to the European theater, represented millions of American workers whose dedication made advanced weapons technology possible. The transition from peacetime consumer goods manufacturing to military production required fundamental changes in worker skills, quality standards, and production procedures. Morrison's training program included 6 weeks of instruction in precision machining, pressure system assembly, and quality control procedures that exceeded anything required in commercial manufacturing. Learning to make military equipment was completely different from civilian work, Morrison recalled in post-war interviews. Every component had to meet exact specifications because soldiers' lives depended on our work. We learned to use measuring instruments and follow procedures that were far more demanding than anything in civilian manufacturing. The psychological impact of defense work affected workers who understood that their products would be used to kill enemy personnel while protecting American troops. This awareness created emotional pressures that did not exist in peacetime manufacturing, requiring management approaches that addressed workers' concerns about their role in warfare. Plant supervisor William Patterson developed worker support programs that balanced production requirements with emotional welfare. Our workers needed to understand the importance of their work for American troops while coping with the knowledge that our products were weapons designed to kill enemy soldiers. We provided counseling and information programs that helped workers maintain morale and productivity. Quality control procedures for military manufacturing demanded precision and attention to detail that exceeded commercial standards by significant margins. Flamethrower components required tolerances measured in thousandths of an inch, with rejection rates for defective parts approaching zero due to the life and death importance of reliable operation. Rose Martinez, employed as a quality control inspector at the Chicago facility, underwent training that qualified her to detect variations invisible to the naked eye. We learned to use precision measuring instruments that could detect differences smaller than a human hair. Components that would have been acceptable for civilian products were rejected if they didn't meet exact military specifications. The integration of female workers into traditionally male-dominated manufacturing roles required changes in facilities, training programs, and workplace procedures. Women demonstrated proficiency in precision assembly work and quality control tasks that proved essential for military manufacturing success. Mary Sullivan, who supervised a predominantly female workforce assembling ignition mechanisms at the Ronson Corporation's Newark facility, observed the capabilities that women brought to defense manufacturing. Women workers showed remarkable attention to detail and quality consciousness that was perfect for precision assembly work. Many had experience with detailed handwork from civilian employment that translated well to military manufacturing requirements. Training programs for defense workers emphasized both technical skills and security procedures necessary for protecting classified information and manufacturing techniques. Workers with access to technical specifications required security clearances and specialized training in protecting sensitive information from enemy intelligence gathering. The speed of wartime production expansion created challenges in maintaining quality standards while meeting urgent delivery schedules. New workers required training while production continued, forcing manufacturers to develop procedures that balanced training requirements with production demands. John Peterson, training director at the Victory Aircraft Plant in Toronto, developed accelerated training programs that prepared workers for complex assembly tasks in minimum time. We had to train workers quickly while maintaining quality standards that could mean the difference between life and death for combat troops. Our programs combined classroom instruction with hands-on training that prepared workers for their responsibilities in minimum time. Worker morale programs became essential for maintaining productivity during extended wartime shifts, when workers faced personal stress from family members in combat zones. Management developed support programs that addressed workers' concerns while maintaining focus on production requirements. The United Auto Workers Union played crucial roles in maintaining labor stability during wartime production expansion. Union cooperation with management created productive relationships that balanced worker welfare with production requirements while avoiding strikes that could have disrupted military equipment deliveries. Union Representative Walter Morrison served on joint labor management committees that addressed worker concerns while maintaining production schedules. Our members understood the importance of flamethrower production for American troops overseas, but they also needed assurance that their welfare and working conditions were being protected. Cooperation between labor and management made it possible to achieve both objectives. Shift work requirements for continuous production created challenges in maintaining worker health and productivity during extended operations. Many defense plants operated 24 hours daily to meet military production demands, requiring careful scheduling to prevent worker fatigue that could affect quality or safety. Plant nurse Patricia Anderson developed health monitoring programs that identified workers experiencing fatigue or stress-related problems before they affected production quality. Extended shift work created health challenges that we hadn't encountered in peacetime manufacturing. We learned to monitor worker wellness and provide support services that maintained both worker health and production quality. Safety considerations for defense manufacturing included hazards from handling flammable materials, high-pressure testing, and precision machinery that exceeded normal industrial risks. Specialized safety training and equipment were required to protect workers while maintaining production efficiency. The DuPont Chemical Facility in Wilmington, which produced napalm thickening agents, implemented safety procedures that addressed unique hazards of handling flammable chemicals. Working with napalm components required safety measures far exceeding normal chemical manufacturing standards. Every worker needed training in fire prevention and emergency procedures to protect themselves and their co-workers. Community support for defense workers included housing assistance, childcare services, and transportation programs that helped workers cope with wartime conditions while maintaining productivity. Local governments and civic organizations developed programs that supported defense manufacturing while addressing community needs. The city of Newark, New Jersey, established support services for defense workers that included priority housing, subsidized childcare, and public transportation schedules coordinated with shift changes at defense plants. These programs helped maintain stable workforces while supporting families coping with wartime pressures. Post-war adjustment for defense workers required retraining and placement assistance as military production ended and manufacturing returned to civilian products. Many workers had developed skills and experience that qualified them for positions that had been unavailable before the war, creating opportunities for career advancement. Women workers faced particular challenges during post-war transitions as employers often preferred to hire returning veterans for positions that women had performed successfully during wartime. However, many women had discovered capabilities and interests that influenced their career decisions and family planning for decades afterward. Betty Wilson, who had supervised ignition cartridge assembly at the Ronson facility, used her wartime experience to establish her own precision manufacturing business after the war. Defense work taught me skills and confidence that I never would have developed in traditional women's employment. The experience opened opportunities that changed my entire life and career. The technological knowledge gained by defense workers contributed to post-war industrial development as workers carried advanced manufacturing techniques into civilian employment. Many innovations developed for military manufacturing found applications in consumer goods production, contributing to post-war economic growth and technological development. Captain Patricia Anderson moved through the forward aid station on Iwo Jima with practiced efficiency, directing corpsmen treating the steady stream of flame warfare casualties arriving from assault operations against Japanese cave systems. As Chief Medical Officer for the 5th Marine Division, Anderson had developed specialized procedures for treating napalm burns that saved lives while maintaining forward medical support under constant enemy fire. The nature of flame warfare casualties required medical techniques that differed significantly from conventional combat injuries. Napalm burns created unique treatment challenges due to the fuel's adherence to skin and its tendency to continue burning until physically removed or smothered. Traditional burn treatment methods proved inadequate for injuries caused by military flame weapons. Hospital corpsman First Class Robert Martinez had treated over 200 flame casualties during 6 months of Pacific operations and understood the critical importance of immediate treatment for napalm exposure. The first few minutes were crucial for survival. Napalm would stick to skin and continue burning, so our immediate priority was removing any remaining fuel and stopping the burning process. Pain management and shock prevention came next. The development of portable burn treatment kits provided medical personnel with immediate treatment capabilities specifically designed for napalm casualties. These kits included specialized bandages, cooling agents, pain medications, and fluid replacement supplies that could be administered in forward positions before evacuation to surgical facilities. Medical supplies for flame warfare treatment required specifications that addressed the unique characteristics of napalm burns while remaining portable enough for forward deployment with assault units. Standard military medical supplies were inadequate for treating injuries that covered large body areas and required immediate intervention. Lieutenant Commander William Thompson, commanding the Naval Medical Research Laboratory, developed treatment protocols specifically for military flame weapons casualties. Napalm burns differed from conventional fire injuries in extent, depth, and chemical composition. We had to develop new treatment methods that addressed these unique characteristics while remaining practical for battlefield medical care. The psychology of treating flame casualties affected medical personnel who witnessed the devastating effects of projected fire weapons. Corpsmen and medical officers required emotional support and specialized training to cope with injuries that were more severe than most conventional combat wounds. Combat medic Thomas Rodriguez described the emotional challenges of treating flame casualties during Okinawa operations. Napalm burns were among the worst injuries we encountered in the Pacific. The extent of damage and the suffering involved affected everyone in the medical chain. We needed support systems to help medical personnel cope with what they were seeing and treating. Evacuation procedures for flame casualties required modifications to standard medical evacuation protocols due to the immediate treatment requirements and pain management needs of burn patients. Standard ambulances were inadequate for patients requiring continuous fluid replacement and specialized burn care during transportation. The development of specialized ambulances equipped with plasma, morphine, and burn treatment supplies provided casualties with immediate medical care during evacuation to surgical facilities. These vehicles were staffed with corpsmen trained specifically in burn treatment techniques and equipped with communication systems that allowed coordination with receiving hospitals. Field surgical procedures for flame casualties required techniques adapted for treating extensive burns under field conditions with limited resources. Forward surgical units developed procedures that balanced immediate survival requirements with long-term treatment needs while working within logistical constraints of combat operations. Major David Miller, commanding a forward surgical unit supporting Marine operations, developed field treatment techniques that significantly improved survival rates for flame casualties. We learned to provide immediate surgical care for extensive burns using portable equipment and limited supplies. These procedures prevented shock and infection while preparing casualties for evacuation to facilities with more comprehensive treatment capabilities. The training of medical personnel for flame warfare casualties required specialized instruction in burn physiology, pain management, and psychological support techniques. Standard military medical training was insufficient for treating injuries caused by military flame weapons under combat conditions. Medical schools established specialized courses for military medical personnel that addressed the unique requirements of treating flame warfare casualties. These courses included instruction in burn treatment techniques, pain management protocols, and emotional support methods for both casualties and medical personnel. Research into burn treatment techniques accelerated during the war as medical personnel gained experience treating napalm casualties. Military medical research facilities conducted studies that advanced understanding of burn physiology and treatment methods with applications extending beyond military medicine. The Naval Medical Research Institute conducted comprehensive research into napalm burn treatment that influenced civilian burn care for decades after the war. Their research contributed to improved understanding of burn shock, infection prevention, and reconstructive surgery techniques. Dr. James Wilson, directing burn research at the Naval Medical Research Institute, documented advances in treatment techniques. Military experience with napalm burns accelerated our understanding of burn physiology and treatment methods by decades. The techniques developed for treating military casualties became standard procedures for civilian burn care and influenced medical education worldwide. Long-term rehabilitation for flame warfare casualties required specialized facilities and programs that addressed both physical disabilities and psychological trauma. Veterans Administration hospitals developed comprehensive rehabilitation programs specifically for burn survivors that included reconstructive surgery, physical therapy, and vocational training. The complexity of treating flame warfare casualties created demands for specialized medical personnel that exceeded normal military medical requirements. Additional training programs and recruitment efforts were necessary to provide adequate medical support for operations involving extensive flame weapon employment. Psychiatric treatment for flame warfare casualties included both immediate battlefield support and long-term therapy for psychological trauma associated with burn injuries. Many casualties required extensive counseling to cope with physical disabilities, changed appearance, and memories of their injuries. Captain Robert Hayes, a psychiatric consultant treating flame warfare casualties, developed therapy techniques specifically for burn survivors. Flame warfare casualties faced unique psychological challenges including altered body image, chronic pain, and traumatic memories of their injuries. Treatment required specialized techniques that addressed these specific problems while supporting overall recovery. General Douglas MacArthur stood on the deck of the USS Missouri in Tokyo Bay on September 2, 1945. watching Japanese officials sign surrender documents that formally ended World War II. Among the factors that had compelled Japanese capitulation was the devastating effectiveness of American flame weapons, which had proven decisive in reducing fortifications that conventional weapons could not neutralize. The strategic impact of American flamethrower development extended beyond immediate tactical victories to influence post-war military doctrine, international law, and technological development worldwide. The success of American flame weapons demonstrated the importance of innovative weapons technology while revealing the terrible human costs associated with such effectiveness. Intelligence assessments conducted immediately after Japanese surrender confirmed that American flame weapons had significantly influenced Japanese strategic calculations. Captured documents revealed that Japanese commanders recognized their inability to defend against weapons that could neutralize their most sophisticated fortifications with minimal American casualties. Lieutenant General Yashijiro Yumizu, chief of the Japanese Army General Staff, acknowledged during post-surrender interrogations that American flame weapons had been decisive in breaking Japanese defensive capabilities. The American fire weapons made our traditional defensive methods obsolete. Positions that could withstand artillery bombardment and infantry assault were vulnerable to flame attacks that forced abandonment or death by burning. We had no effective countermeasures. The technological superiority demonstrated by American flamethrower development influenced post-war military research and development priorities in numerous countries. Nations recognized that innovative weapons technology could provide decisive advantages that overcame traditional military capabilities and strategic positions. Soviet military leaders, analyzing American flame weapon effectiveness, initiated development programs designed to match or exceed American capabilities. Marshal Georgy Zhukov personally authorized research into advanced flame weapons that would influence Soviet military doctrine throughout the Cold War period. British military analysts concluded that American flame weapon success demonstrated the importance of integrating civilian research capabilities with military development requirements. The collaboration between universities, commercial manufacturers, and military organizations had produced technological breakthroughs impossible through traditional military research alone. The international legal implications of flame weapon employment became subjects of extensive debate as nations sought to establish standards for weapons that had proven both effective and controversial. The Geneva Convention protocols developed during subsequent decades would eventually restrict incendiary weapon use against civilian populations. Medical advances developed for treating flame warfare casualties found extensive applications in civilian burn care and emergency medical treatment. The specialized procedures and equipment developed for military use contributed to improved medical capabilities that benefited civilian populations throughout the world. Dr. William Thompson, Director of Burn Treatment Research at the Veterans Administration, documented the civilian applications of military medical advances. Techniques developed for treating napalm burns revolutionized civilian burn care and emergency medicine. Military research accelerated medical understanding by decades and saved countless civilian lives through improved treatment methods. Industrial production techniques pioneered during flamethrower manufacturing influenced post-war defense production and civilian manufacturing. Quality control procedures, material science advances, and production coordination methods developed for military applications found widespread civilian applications. The psychological warfare aspects of flame weapons influenced military doctrine and strategic planning throughout the Cold War period. The terror effects demonstrated against determined enemies suggested applications for future conflicts where similar psychological advantages might prove decisive. Educational institutions worldwide studied American flamethrower development to understand the organizational and technical factors that had produced such remarkable success. Universities established research programs that built upon wartime technological developments while training personnel for post-war military and civilian applications. Environmental considerations related to flame weapon employment became increasingly important as nations recognized the long-term effects of napalm use on ecosystems and civilian populations. These concerns influenced international agreements restricting incendiary weapon employment and development. The human cost of flame warfare, documented through casualty statistics and medical research, contributed to understanding the true price of military effectiveness. Post-war analysis revealed that technological superiority achieved through innovative weapons development required acceptance of moral and ethical considerations that extended beyond immediate military objectives. Veterans of flame warfare continued to grapple with physical disabilities and psychological trauma decades after the war's conclusion. Their experiences provided insights into the long-term human consequences of technological warfare that influenced military planning and medical care for subsequent generations. The success of American flamethrower development demonstrated that innovative military technology could achieve decisive advantages that overcame seemingly impossible tactical challenges. However, this success also revealed the terrible human costs associated with such effectiveness, creating moral and ethical questions that would influence military doctrine for generations to come. The legacy of World War II flame warfare extended far beyond immediate military applications to influence technological development, medical care, international law, and human understanding of warfare's true costs. The weapons that had proven so decisive in breaking Japanese resistance would continue to shape military and civilian life throughout the post-war world. As American forces prepared for occupation duties in Japan and demobilization at home, the lessons learned from 4 years of flame warfare development would influence military doctrine, technological research, and international relations for decades to come. The revolution in projected fire weapons had changed warfare forever, leaving a legacy that extended far beyond the battlefields where they had proven so devastatingly effective. The story of flamethrower development during World War II represents one of the most significant technological and tactical innovations of modern warfare. From the failing M1 systems of 1942 to the revolutionary M2 weapons that dominated Pacific battlefields, American engineering and industrial capabilities had produced weapons that changed the nature of infantry combat forever. The human cost of this technological revolution, measured in the lives of operators who carried these weapons into battle, the enemies who faced them, and the civilians who witnessed their effects, serves as a permanent reminder that military effectiveness comes at a price that extends far beyond immediate tactical victories. The flame weapons that had proven so decisive in ending World War II would continue to influence military technology, international law, and human understanding of warfare's true nature for generations to come.